Okay, let's get this party started. Thank you for the light. Okay, so this afternoon should be exciting for everybody in the room. All the model developers, the CI team, the PPRP. So we're going to start. We have until, let me look at the schedule. We have the next 2 hours for Nico to try to go through all his slides. So we've separated it in 2 talks and 1 hour discussion. That's not how it's going to go. It's going to go, we have 2 hours, and his challenge is to make sure he goes through all the material, and we welcome discussions and questions. We want people to understand. So at the beginning, if you kind of get it, let it go, so we have some time to go when it gets really complicated. Okay? So Nico, take over. I'm going to share screen. Okay. And then, there you go.
Okay, so in the beginning, we're just going to compare the GMPEs, so all the ones that were submitted or that you heard about yesterday and today. And I'm just going to show some plots of their scaling versus magnitude and distance. And then we can look at them together, or every model developer can see where his model falls with respect to the other ones. So the way that worked is that the developers provided GMPE predictions at 4 frequencies, 1 Hertz, 5 Hertz, 10 Hertz, and 100 Hertz or PGA. That depends on the model, at 4 different magnitudes, and at 1, 2, 3, 4, 5, 6, 7, 8, 10 different distances. And depending on the model, the distances are either RUP, RJB, and or epicentral distance. We need to keep that in mind when we're comparing those, because they're not totally direct, because each of those, so I have predictions at RJB 10 or predictions at RUP 10. In total, there are 15 GMPEs from 9 modeling groups, and in addition, there are the 10 EPRI component models and the 4.5 clusters that they had, or the 4+1 or clusters. These are the new sets of GMPEs. Dave Boer provided 6 sets of predictions based on stochastic simulation. You all heard that yesterday. His model is an RUP model. He provided predictions for VS30 3,000 meters per second and 100 Hertz PSA. And these are his names. So these are the names of his 6 different models. We have the model from Art Frankel, which is also based on RUP and is given for 100 Hertz and at 3,000 meters per second. I also received predictions from the model of Tavakoli and Pezeshk from 2005, an RUP-based model at VS30 2,900 meters per second and PGA. Vladimir Greiser provided 2 models, his EPRI model and his newer model, and he provided predictions at 760 and 3,000 meters per second. We have the model of Hassani and Atkinson. That was given for RGB from 1 to 400 kilometers, and at VS30 760 and VS30 greater than 1,500 meters per second. Yeni and Atkinson, VS30 760 and greater than 1,500 meters per second. Then we have the L. Noman and Kramer model, epicentral distance based at VS30 760 and 3,000 meters per second. The Pezeshk et al. Model, the Chajouet and Pezeshk model, and I actually changed that in the other one, so it's SP14. And we have the PIA model. And there are 4 versions of the PIA model, and these are based on the different extrapolations, so Grades and Pitaka, GP and XM, And then we have one which is Arkansas and Oklahoma, and the other one that's all the rest. And I'm only plotting the models at CS30 is 3,000 meters per second, or 1,500, or for the I'm only plotting them for the harder site conditions, which is more uncertain because the bulk of the data is not at 3,000 meters per second, so that's also something to keep in mind, that the extrapolation to those hard rock conditions is more uncertain, but that was the TI team request, so it's only plotted there. In addition, there are the EPRI models. I just copied this slide from Bob Young's presentation from the last workshop. There are 4 clusters, and in the first cluster there are 4 models. Then in the second cluster we have 2 models, and the clusters are based on method and not based on, they're just based on method. So in the first one we have single corner Boone source models. In the second one we have called complex empirical source models. Then we have the models with geometrical spreading R to the power of minus 1.3. I'm sorry. And in the end we have the 2 summable models. So there are 2 versions of cluster 4. One is for rifted and the other one is for non-rifted. And now we need to go to these things. So now that's a lot of plots. So we have 19 models, 10 EPRI models, plus 5 clusters. So that's like 44 different lines that we can plot. So I have this thing, I hope it works, where we can just click on different models and then see how they compare. And we can go through the different distances and go through different frequencies. And there are thousands of different possibilities to combine all these models. So I don't think we have even 2 hours would be too long to go through all of them. But I don't know what you want to see. Do you want to just see all the new ones, or the... Unfortunately, I can select, I have to click through all of them, but so I can, one thing I should say, so this corresponds to the clusters, and the clusters are plotted as median is the solid line, and then the 5th and 95th percentile is the dashed line. So that would be the 95th percentile of the first cluster, of the first EPRI cluster. And on the left we have the new models, and on the right we have the EPRI models.
But let's start at like 100 kilometers instead of 1,000.
Right. 100 kilometers, 100 hertz, and so these are the 6 Bohr models in comparison with EPRI, the first EPRI cluster. So the one that's high is this one. Right. And then we can add the Frankel.
That's one that we were talking about the other day, of having the magnitude scaling, and we're not sure it's implemented right. And this is another indication it's sticking out too high, right?
Okay. Oops. So the Frankel, I don't know if you see that the Frankel model was added here. And it stops here because we only have predictions at magnitude 7. And how about, do you see that when it pops up?
Only if you click back and forth,
right.
You can see where it is.
Okay, so there it is. That's the Tabakolin Pelzesh. Then the 2 Greiser models, which are relatively low.
Can I make a suggestion to simplify this? just so people see where the models fit, just leave the cluster one for now.
Yes.
And click one at a time so people,
Okay.
they all want to see their own model.
Right, that's,
Let's start, we'll look at all of them together
No.
also. Yeah.
right. So this is cluster 1, and that's the AB14 Bohr model. Let's just call it that. So let's plot there. This is the next one.
I don't think since you only have one, you don't need to double check it.
Okay. Oh, someone, sorry. So yes. So do you want me to go back? Okay. Okay. Okay.
Only
So here we
forward.
have the Hassani and Atkinson, Yinyi and Atkinson, Norman and Kramer, and that's the SSHAC et al., the Chargouet and SSHAC. And we don't have the peer model at 100 hertz. So right. Okay.
You said you only have the peer model at 100, but you...
No, we don't have it at 100.
Ah, okay, yes,
We don't
sorry.
have it. So that's AB14 Bohr.
Okay, so let me go back and follow up on Gail. She wanted to see the whole shebang. Just turn them all on for now to see the cloud and where the lines, the range, and then we can flip through the different frequencies and a couple distances. Okay, and then every clusters as well. Yeah, you want to see the whole thing? We'll look at the whole thing.
I mean, one of the nice things there, even though it's kind of crowded, there are a lot of different magnitude scalings there. So the lines cross, which is good, because that's a lot of, or it means there's a lot of epistemic uncertainty that we're capturing with these different models.
And behaving well in that the magnitude, it should spread to the right,
Yes.
which it does.
With them all turned down, just go through your different distance and frequencies up at the top.
Okay.
Just flip through them.
So it's 10 kilometers, 100, 500, 1,000. I just go 10 at 5 hertz, 100, 500, and 1,000. 1 hertz, 10 kilometers, 100 kilometers, 500, and 1,000. Any more requests?
It's $5 per model. We're raising money.
This is why we're doing Salmon's map, okay? Because there's so much to look at, and they're trying to find a way to throw all this into one picture. But what you may want to be thinking of are which are the models that are sticking out, either in their slopes or their amplitudes, because then when you're looking in the maps, we can think about where they are again. So what's...
So these two, these are the,
We're going to stay away from 1,000. So,
yeah.
Yeah, look at the, one hertz, the other distances. Okay, that's good.
So that's what distance, the magnitude scaling. So I have the same
Okay.
thing for.
So now we can look at the distances. Magnitude 6 or 7? 6. Okay. Boer, BCA 10A from Boer, 10D from Boer, BS11 Boer, J97 Boer, SO2 Boer. That's the Franklin model. Tavakoli and Bezeshk, Greiser EPRI, Greiser NGA East, Hassami and Atkinson, Yenye and Atkinson, Norman and Kramer, Bezeshk et al., Chajouet and Bezeshk, and we don't have those models, 100 hertz. I think I can click them anyway. Oh, yes.
Yeah, just one comment there. So there's no saturation, magnitude 6, and there's even some steepening of the slope at short distances. That's probably RJB and our rupture issues by Daypool,
No.
or what's causing that?
Yeah, it's the 1.3.
Yes. That should be the 1 point.
So the 1.3 model, steeper. And,
It's starting at R RUP equals 10, so you're not seeing any saturation to the left of that.
One of the things we also need to keep in mind, it's plotted as, so we have prediction at 10, 20, 50, 100, 200, 500, so we cannot really see a finer detail. For example, if somebody includes moho bounds or something, we don't see that in these plots. Or we would see it only very approximately. Okay. So that's magnitude 5, magnitude 6, 7, and 8.
slow down.
Okay, I'm
Just
sorry.
so we digest
Right.
all the money.
So this is at 10 hertz.
5
5.
and 10. Yes, that's where, that's
6, 7, and 8. And that's 5 hertz. Magnitude 6, magnitude 7, magnitude 8. And then we have 1 hertz, magnitude 5, magnitude 6, magnitude 7, and magnitude 8.
Okay, can I make a proposal for moving forward? The juicy part is really the math. So I think we should look at the math, and we have these tools there. If we see something we don't fully understand, then we can just select the models we see that are different. So we'll use, we know this exists, it's in the background. Is that cool?
And that's on the web page, right? So
I haven't put it on the web page yet, but yeah. So people, so we can put those. We have no problem sharing that. It's as long as the GMP developers are okay with it. So that's what we need to make sure. But within the project, at least we can share. So what Nico has created is our small applications that you need to download the Wolfram mathematical plugin. It's free, and then you can do that on your own computer and have fun. So the PI team had access to that, and GMP working group as well. Okay.
well, Ken told me that it didn't work on Windows or didn't look good on Windows. I'd look into that and maybe I can fix it.
Oh, Vladimir got it to work.
Okay, well,
Ken, you can ask Vladimir how he did it.
How do you do that? How do you? Yeah, I don't know. I didn't do anything. Go back to the presentation.
Yeah. Is that the one? Okay.
No. Right. Now, sorry. Okay, so now what we're going to do is, we're going through application of Hammond's map to those models. And Norm just said why we're doing that is there are 44 different models, and it's really hard to look at them in these plots and capture the gist of what's going on. It's really hard in Hammond's maps as well, so I'm not sure, but we can still compare them, and we can still easier maybe make out clusters or digest which models are really sticking out. First, I'm going through an introduction. I made that pretty extensive, but if it's too easy, then you can just tell me to move on. And then we'll come to the visualization of the NGAEs and EPRI models. So we have, I've got Hammond's maps for all of those for the different frequencies. And in the end, I'll talk about extrapolating the model space, or extrapolating and interpolating the model space. Okay. So the motivation for both using Hammond's maps, but also the general motivation of this work is to capture the range of the epistemic uncertainty in the median predictions from the possible models, not just from the published ones. So this is a plot. So what we have here is log PSA at 10 Hertz for magnitude 6 and 200 kilometers from the 19 proponent models. And these are these red dots. For the red dots, you don't need to care about the y-axis. But the thing is, these are just 19 discrete points, but why should this ground motion prediction should not be possible? Or why should we have a model over here? So the basic assumption is that we have, in reality, that we have a continuous distribution over a certain space, and it's centered somewhere, and it has a center, body, and a range, and it would be much easier to work with this continuous distribution. So what I just did here, I just fitted a normal distribution, so basically just mean and standard deviations, to those 19 predictions and plotted the PDF. Over that. And you can just work easily with a normal distribution. You can just discretize it and say, okay, I take the mean, give that 60% plus minus sigma, give that each 20%, and that's very easy. And if the hazard is only coming from a magnitude 6 event and in 200 kilometers, then we're done. And it's just easy. That's just easy. We just fit this. We just define this normal distribution. We might play around with it a little bit, but based on the current models, we just define it, discretize it, we're done. Problem is, if we have more than one magnitude distance combinations, which we usually have, what do? So you could go through all of those possible magnitude distance combinations, do the same thing, but then you're losing the correlation between them. You might have a model that's low at magnitude 6, but high at magnitude 7. And if you just go through one single normal distribution or one single distribution at each magnitude distance combination, you're basically just fitting it, and then you select ground motions from that. It would correspond more or less to a scaled back bound approach, taking the mean, taking some percentile of that. We don't want to do that, or I don't know. So the basic idea is we take a finite number of GMPs, 19, 29, however many we have, and then we interpolate and extrapolate between those. And that gives us a continuous distribution of GMPs. And this continuous distribution should have models that both differ in up and down scaling, but also differ in magnitude and distance scaling. So we should have models in there that have a different magnitude scale, and that scale differently with distance, and maybe even scale different with VS30 and so on, if we care about that. In the end, if we have a continuous distribution, that actually would be really nice, but to run it on a computer, we need to discretize that to get a manageable number of models. So therefore, we want to take this whole continuous distribution of GMPs and partition it into clusters of maybe 10, 20 models. And the clusters should be defined on the similarity of ground motion predictions. And we don't want to, clusters should be based on the similarity of the predictions, and not just based on the on the method or who was developer or who comes from the US and who comes from Europe or something. All right. So the question is, how can we partition the GMPs into clusters? So first, what we need to do is we need to define similarity between GMPs. And we need to, there are several ways to do that. We discussed that briefly yesterday. And we also need to find, if we have this continuous distribution, we need to know how do we discretize it? How do we know where to define the clusters that we need? And before we can do that, we need to have this continuous distribution. And so therefore, we need to extrapolate the GMPs. And I'll just go through everything over there. So this is just one of the plots that we've seen before. 40-something lines on that. How do we define similarity between GMPs? How do we partition these 41 models into 10 or into 5 different models? It was really hard to do, especially if you then go over through all the different magnitudes and distance combinations. Okay. So I'm going to step back and have a very, very simple example. This is just random samples from 3 two-dimensional Gaussian distributions. And I plotted just the first coordinate versus the second one. And there are clearly 3 well-defined clusters in there, and we can just go there and say, okay, well, all these points are much closer together than they are to these points and to these points, so we have one cluster here, one cluster here, and one cluster here. It's very, very simple. We just base it on the distance between the x and y coordinates. And I defined the distribution so that it would give a nice cluster. The problem becomes harder when we go to higher dimensions. So that was a 2-dimensional Gaussian distribution. I could plot that in 2D. What if we have a 4-dimensional, a 10-dimensional Gaussian distribution? We cannot plot that anymore. So that generally things get harder when the dimensions get harder. Mainly because we can't plot them, or not mainly, but one of the reasons is we can't plot them. So one of the ways to deal with this is just to project them onto a map. We do that every time when we look at Google Maps, for example. That's a 2D representation of the globe. And it's just easier to work in 2 dimensions than it is to work in 5, 10, or 20 dimensions. So this is just an example. These are random samples from 3 4-dimensional Gaussian distributions. And since I can't plot them, I just plotted the first and the second coordinates. All these different clusters overlap. But I defined them so that they still form nice clusters in 4 dimensions. But what I can do is I can project them from the 4 dimensions into 2 dimensions. And what that means, using Salmon Smith, I'm coming through how exactly that's working. But now we have nice, well-defined clusters. So the colors represent the 3 different distributions. We're projecting them onto a map, but this map in 2D, but this map is somehow, how do you say that? It's not, it might be wiggled, but it also is not aligned with the coordinates of the 4 dimensions anymore. So if you just had 3 dimensions, so then it would be somehow, would have an angle to all these different coordinates. That's why the different coordinates now in 2D don't have a meaning anymore. Or just we can rotate that, we can mirror it, but what has a meaning is the relative position of these points. So basically what we've done here, we've taken a 4-dimensional space and projected it into 2 dimensions. And it works nicely. We can see the clusters that we defined beforehand. And we want to do the same thing using the GMPs. So we're doing that using Salmon's map, and the basic idea is that we find the configuration of points in 2D such that the distance in 2D is the same as the distance in high dimensions. So we can define, or there's always some distance metric in a higher dimensional space, and then we're just putting the points on the map, and then perturb them as long as the configuration 2D represent, or the distance distribution between all the points in 2 dimensions corresponds to the distance distribution in the high dimensions. Sometimes that works really well if the data is just, so if the data forms some lower dimensional manifold, so if the data is approximately on a plane, that works pretty well. Sometimes it's just not possible, because if the data fills up the whole space, we cannot, there's no way we can project it. Okay. To do that, we need to represent the ground motion prediction equation as a point in high dimension. And that's actually pretty simple. Basically, we're just discretizing the GMPE. The GMPE is a function, and then we just evaluate that at different magnitude and distance grid points. So valuing magnitude 5 at 10, 20, 50, 100, 500 kilometers, magnitude 6, and the same distances, magnitude 7, and so on and so on. That gives us, so for the flat file that we had, 28 different ground motion predictions. So 28 different ground motion values. And then we're just saying this is a point in a 28-dimensional space. So each of the coordinates in that 28-dimensional space corresponds to a ground motion prediction at a particular magnitude and distance value. And then we're just going to take that high-dimensional space and project it into 2 dimensions. So this is one example. So here we have the SSHAC model. We're just evaluating it at those different points and take these predictions as our coordinates for that particular GMPE. Okay. This is an example of a 2-dimensional GMPE space or ground motion space. This is not a map. This is an example of the space. But so here we have log PGA for magnitude 5 and distance of 100 kilometers, and here we have log PGA for magnitude 6 in the distance of 100 kilometers. And these are all the different GMPEs that were plotted before. That includes the new component for the new NGAEs models, the EPRI models, and the clusters. And there actually is information even in this plot, even though it would be easier to look at it in a traditional way, plotting it versus magnitude, but there's information about the differences between different models. So for example, these 2 GMPEs Each of these points corresponds to a GMPE. But these two GMPEs have the same prediction for magnitude 5. But they have a very different prediction for magnitude 6. This one has a much larger prediction than this one. That means that this one has a steeper magnitude scaling. This model has a steeper magnitude scaling than that one. On the other hand, if we just compare these two, I go roughly the same distance in ground motion for magnitude 5 and in ground motion for magnitude 6. That means this model is more or less just an upscaled version of this model. Okay. The nice thing, what we see is they don't align on the diagonal. That means there's some differences in magnitude scaling between magnitude 5 and magnitude 6. That's good, because otherwise we wouldn't have any epistemic uncertainty in this. There's also other things we can think about from this plot. So for example, we don't have any points over here and we don't have any points over there. And that's because these are unphysical. If we had a point over here, that would mean we would have a model that predicts the ground motion at magnitude 6. That is, I don't know what exactly the number is, 10 times as large as the ground motion at magnitude 5. That would be unphysical. So basically, we can define some range in here where we have physical models, where we should have physical models. And that would probably be somewhere around here. We can also say, why do we not have a point here? Why do we not have a point here? It's just, these are still possible models if we just define our possible model space to be maybe this part of this ground motion space. And then we could go ahead and take this, even though nobody has published a model that predicts these PGA values, it should still be a possible model. And then, so that means we can, based on the model space, there's some structure in the overall ground motion space, and that the physically plausible GMPEs don't fill up the whole space. They fill up a much smaller subspace. So our goal is to get at this smaller subspace. And the basic assumption is that we can project this subspace into 2D. Is that kind of clear what I tried to say? Okay. So basically, that means there's some structure in the higher dimensions. Okay, when we go to higher dimensions, the same structure should be there, right? We just go in different directions, and then we see, okay, if we now add one coordinate for magnitude 7, we can do the same thing, saying, okay, two models have the same predictions at magnitude 6, but a different prediction at magnitude 7. So they're at different points in the three-dimensional space now. But that should correspond to relative differences on the map. So basically, the relative differences in these higher dimensions correspond to the relative differences on the map. So how do we define the distance between the two GMPs? We need to know how to do that, and if we just define the ground motion space as we did before, then a natural distance would be the Euclidean distance in that space. And the Euclidean distance would mean the sum over the log PSA values for magnitude for GMP I minus the log PSA values for GMP J, the squared sum over that, and take the square root. We discussed yesterday, this gives the same weight to each of the coordinates. So basically each magnitude distance pair, or the difference at each magnitude distance pair, is equally important. So the difference between two GMPEs for magnitude 5 and 1,000 kilometers is as important as the difference for magnitude 8 and 10 kilometers. Rob.
Don't want to get lost here. What does K represent there?
K represents the sum over the different magnitude distance combinations. So right, I should have explained that here. So basically, in this case, this would be K1, this difference, this would be K2, K3, K4, and so on. So we're just summing up the square of these differences, and then take the square root of those.
And this would be done for each ground motion metric?
Right. So for each different GMP. So that gives us, in this case, if we just take this one as 1, 2, 3, 4, as a 7-dimensional space, then the squared sum of these differences would be the square of the Euclidean distance.
We are dealing with each spectral frequency completely independently at this time. We tried putting them together, and that really blurred things too much that you couldn't see what was going on. So he's going to make a completely separate map for 1 hertz and for 10 hertz and so on.
Can I ask a question? At some point, if I remember correctly, you were fitting a common functional form and then doing this analysis of the coefficients.
We did not do that on the coefficients. We still did it for the ground motions.
Okay.
So for each sampled model of the common functional form, we created ground motion predictions and then defined the distance based on the ground motion prediction.
But always on the ground motion prediction,
Right.
never on the coefficients. Okay.
No.
While he's going to see Art, one of the issues again was, what's the right metric to use to describe the difference? And this is one, and we had talked a year ago in the Swiss meetings about using the aggregation to weight them, or maybe there's some other metric that could be used. So there's multiple ways you could do that.
Another question is, would you, instead of using the square of the difference, just use the difference? In other words, to sort of preserve which is higher and which is lower? Or is that not realistic?
The thing is, if you use the squared, so if you don't use the squared difference and not even the absolute difference, you could have, it's not realistic for ground motion, but you could have a model that goes like this and a model that goes like this, and that would have 0 distance. So, so what we ended up, or what was done for Swiss, was to weight these differences, and so don't take these differences, but weigh each of these differences at each magnitude distance combination based on the deaggregation weight. So that should give something that is closer to hazard space than this one. So that would be good if each magnitude distance combination contributes equally to the hazard. Ryan had a question.
Can you tell us what's the main motivation for doing this in the ground motion space in terms of the GMP coefficient space, if you are able to refit them into a common form?
Well, mainly because there are a lot of trade-offs between different coefficients, and so models that are close in coefficient space might not give the same ground motion, even though it's very unlikely actually. But the main reason is that we care about ground motion space and not about coefficient space. So
another comment. So I take the point that you couldn't do it in absolute or in distance average, but I presume you could do it in the equivalent of an L1 norm rather than an L2 norm. And I presume another thing that one could do is pick basically which magnitude distance combinations you wanted to consider in such a thing, and any that you view as being unimportant, you could just simply drop, right?
Right. So So in SWOS, the magnitude distance coordinates were chosen so that that there was a denser spacing for those magnitude distance ranges that were considered important. And then it wasn't done, so I think the maximum distance was 70 kilometers, because beyond 70 kilometers there was no contribution to the hazard.
What Brian, I think the response you would give to Brian is you could have differences in coefficients and get the same ground motion,
yes,
right? And so while we wouldn't want to map them in their difference in coefficients.
The epistemic uncertainty we try to quantify is for ground motion, not for models of space.
Okay, so now that we've defined this difference between GMPEs, and we might change that, or that difference between GMPEs might change, so we might use a different metric. But once we have that in high dimensions, we can just go ahead and apply the Sammons map algorithm. That means we have a difference in high dimensions, and we have a difference on the map, the distance between points on the map, and then we take their difference, and basically that's then sum over all points, and that's the misfit function. So basically we're trying to minimize the misfit between the difference in high dimension and the difference in on the map.
And we've talked about this before, so the summation can look confusing if you're trying to follow the map, because there's a double sum. There's a sum over j and then a sum over I only up to
j.
Half of the matrix, right? That's all it is. So think of that as sum over I, sum over j, but only through half of them.
So what that means is, we need to have a starting configuration on the map, and then we're optimizing this configuration based on this misfit function. Very similar to maximizing likelihood. You have in a nonlinear model, you have starting values for your coefficients, and then you optimize the misfit function, or in that case the likelihood function. But that's basically the same thing. So since the starting coefficient, the starting configuration can be random, that means the map will change anytime I redo it. We redo the map. Because with the random starting combinations, model 1 might at one point start in the upper right corner, and the next starting point would be in the lower left corner, and then based on how that works, it will not end up in the same position as before. But if the algorithm converges, the relative distances, that means the 2D differences, will match the high dimensional differences. That means the coordinates do not have a meaning, but the map distances do have the meaning. Because the map distances correspond to the distance in our high dimensional space.
I think you need to stop and repeat that again, just to make sure, because every time he puts up the map, people say, what are the axes, right?
Yeah. So I did, it was actually your written materials were very clear, thank you. I still think, just as a matter, because every time that goes up, you are going to get exactly the same question. I still think it would be helpful to label the axes with what is the closest no, it doesn't mean nothing, right? So what I've understood from what you presented is that one axis is projected dimension 1, and the other axis is projected dimension 2, and the units in each in parentheses would be, essentially arbitrary distance unit, right? So I think even if it always is the same, well, okay, so no, all right?
I'm sorry,
so
okay.
if I've got it wrong, this is So,
So-
to me,
so
you should
basically-
be able
yes.
to explain, even though I get the point that it's not like, one is PSA and it's in units of centimeters a second and the other is magnitude. The closest you can come to describing those axes would be useful to label them.
Right. But imagine you're giving, somebody tells you I have 3 points in, 100-dimensional space. And 3 points always lie on a plane, so you can perfectly match them plot them on a grid. So the person says, okay, I have these 3 points, and the distances between them is, what's the 100-dimension distance? Let's just say the distance is 1 foot between each of them. That's 30 centimeters. And so then you just go ahead and say, okay, I'll take the first point and plot it at 0. Then you go ahead, okay, you take the second point. Well, where do you plot the second point now? You can plot that anywhere on a circle with 30 centimeter radius around the first point. So you just pick 1 point. But once you pick that 1 point, the third point actually only has 2 possibilities now. Because it's the same distance, so we can plot it. So it's one is here, and we'll just plot it there or there. So we have a 3-sided triangle. But depending on where I plot my first point and my second point, so when I plot the first point at 0, 0, the second point at 0 and 30. Then the third point must be at 15 and square root of 2 times 30. So that's plus or minus that. But if I plot the first point at 0, 0 and the second point at 0, 30, then the third point must be at square root 2 times 30 and 15. But basically, I convey the same information, but I have basically just a rotated map. But now it's just rotated. It's just rotated.
Can I say something? But maybe it doesn't matter. But if all the units are spectral acceleration units, any rotation you do, you don't change the units. Unless you're deforming things.
Right.
Maybe you are.
Yes. No. But we can rotate anything. We can rotate it any way we want. The relative positions don't change, and that's the important thing.
Exactly. Maybe that's the key. But I think if you're in a multi-dimensional space of meters, any direction you take within that space is also in meters.
I'm sorry if that was what you said, and I'm sorry then.
But
I said no.
But I don't think it matters.
Okay, that's exactly then. That's right then.
But
but maybe this is a distraction.
But I want to clarify something that I infer from this. Does it mean that the whatever non-dimensional units are the same for both of those axes?
Yes.
Okay. And I think actually,
Yes.
I think if you do label, as something, you can call them watermelons or something, but, there's 6 watermelons vertically and 6
So
watermelons.
the thing is, the units are not arbitrary because the units correspond to the Euclidean, correspond to the distance in the high dimensions. Of course, we don't think about that, so we don't think about a distance between in ground motion space, but they're not arbitrary.
Units are squared log, natural logs, right? So we could have
So
put
the
down
units
there
of
ln squared. No, it's ln of g, natural log of g squared. That's what it is, because that's what we've taken.
Well, then we take
The g is gone, but I think it's really just ln squared units. When we put residuals up there, we don't say log of g's, we say natural log units. These are simply natural log squared. That's what's on the x and the y axis, and we can label them that way.
So they have the same units as the ground motion residuals.
In this case, if we did L1 norms, it would be in the ground motion residual.
We're taking the square root of the sum, so it's
So it is
actually
it's natural log. It's them units of the
So it
residual.
is natural. See, and especially if it is in something like that, as simple as if it is square root and you're back to natural log units, then when you put that on, I mean, you could even call it, residual units or something like that, and then people will understand that what they're looking at, because if people then understand, okay, like a residual is 0.1 or something, then you get a sense for how far apart, what does it mean if it's this far apart? How far apart is something?
The problem is it depends on the number of dimensions. So if I only have 2 points, then it corresponds exactly to a prediction at that. But if I have 10 points, then I'm summing up 10 differences.
But we could divide by n, and
true.
then it's like a standard deviation or something. Right. Like the mean difference between them. We can do that, right?
Yes.
I think you can do it because, again, the units were original units. If your dimensions were some in meters and some in seconds and whatever, then you couldn't do it. But here, because they are uniform units, before you rotate them, then you can.
Right, because we have ground motions in all different spaces. We could have an additional component number of modulars, or an additional coordinate in the high dimension number of modulars, and then we couldn't do that anymore, or something else. But no, yes, that was it. That's just a very simple example of 4 different curves. In this case, an 11-dimensional space. So we have one curve going there, one curve going there, and then 2 straight curves. And this is the distance metric in high dimensions. And so each of those curves is these are the coordinates of the black curve, and these ones are the coordinates of the red curve, and so on and so on. And you can probably guess what this looks like in 2D. If we just project that down, it looks like this. So it's basically just a rectangle. And what this means is, so if I go from here to here, this difference between these two curves would disappear. That means going along this axis would mean going from here up to there. So along this axis, only horizontal, in this case, models would plot. Whereas if I go, if I just change the red curve, and rotate it like this, it would rotate in this direction. So that's how we can interpret directions, or how it is possible to interpret directions on the space. Is that kind of clear? So, no.
It's easier when you go back to the magnitude.
Right. Yeah. But basically, and this is how we can check that the algorithm has converged. In this case, they're perfectly on the line. So that's the high-dimensional distance metric. So that's the distances in 11-dimensional space, and that's the distance metric in 2-dimensional space. And they're basically the same. So that means that's how we can assess convergence of the algorithm. That's it for the introduction. So I think we now know how we generate these maps, and now I'm just going to do that for the NGAEs and the EPRI models. And it's going to be a bit messy on the map, actually, because we have a lot more points to plot. So what I did is I just took the predictions of the component models, of the proponent models, of the EPRI component models, and of the EPRI clusters. So and I took magnitudes 5 to 7, and distances from 1 to 200 kilometers for one set of maps, and from 1 to 1,000 kilometers for the other set of maps. I only have that for 10 to 200 right now, and I have the other maps in the appendix, because I think we can probably spend a lot of time on that. And I have a different map for each frequency. We have frequencies 1, 5, 10, and 100 hertz. So that corresponds to a 15-dimensional ground motion space if we only go up to 200 kilometers, and 21 dimensions if we go up to 1,000 kilometers. The NGA, or the new NGA East models, are plotted as solid triangles. The APRI component models are plotted as black dots, and the clusters are plotted as minus for the 5th percentile, an open circle for the median, and plus for the 95th percentile. And I rotated the map so that the 5th and the 95th percentile of the second cluster is approximately horizontal. So that should give us some sort of direction. So that's how the first map looks like. That's for 100 hertz. And so what we have, so this is APRI cluster to 95th percentile, and this is APRI cluster to 5th percentile. I know that. And so now these are the proponent models. So these are...
Let me just say that.
Yes.
So on this one, higher ground motions are on the left.
Higher ground motions are more to the left, and lower ground motions are more to the right.
So in the U.S., it's usually low on the left.
Yeah, but you guys are weird. Right, so these are, but this is consistent with SWOS actually. So, yes. So this is how the individual models plot. We have the Vladimir's model were relatively close together, and if you paid attention, and but you could have seen that in the scaling plots, that they were slightly scaled up and down, and that's reflected here. The Neumann and Kramer model plots pretty low. We didn't really see that in the scaling, but I checked, and if you go through all these different distance magnitude combinations, it is on average low. The reason is this is 3,000 and not where the bulk of the data is. Or I'm not saying that's the reason, but that's a good guess. So we always need to keep in mind that we have this extrapolation to hard rock sites. So these are the individual APRI models based on the cluster, and we can already see, so here we have cluster 2. So this is the median of those two models. Well, that's right in the middle. It's not right in the middle here because these two models are RUP models, whereas the APRI model is an RGB model, and I didn't assume the same depth distribution as was used to define the median. And then we have the individual clusters. Colors correspond to the same colors as in the tool. So these are the two Somerville models. That's cluster 2. Black is cluster 1, and red is cluster 3. So now I'm just plotting. We can go back and check with the tool, but here I've kind of plotted the extreme cases on the left and on the right. And so here we have one of Dave's models, and here we have the Kramer model. And this is magnitude scaling, and this is distance scaling. And there should have been a legend here, but I think this is plotted for 100 kilometers, and this is magnitude 6.
So again, I want to remind everybody, all these maps are in prelim models. None of them are final. What we saw that Dave pointed out with the Silva model being high, it needs to be checked. It might not be correct, and that's fair. So Youssef is saying the numbers come from the developers, but I want to say that this is definitely not final. It's just to see where these things plot on the maps now.
I can say that the peer model is very preliminary.
Bob?
I believe the SO2SC model numbers came from Dave Boer and a cluster from him.
Yes.
So not from the developer in
No.
that case.
So.
Well, Dave here is a developer of the SMSIM method, so that's why we call him a developer. Yes. We need to check.
Right, we're going to check those numbers.
One question, Nico. Is there an easy interpretation in this case? I know it varies depending on the problem. For the vertical dimension?
It's not as easy as for the other ones. So when we go in the other direction, we have then differences in magnitude and distance scale. I don't have that here, but I can. Actually, in this case, we will see that later for the different frequencies. That cluster 2, in my view, so the EPRI cluster 2 does not capture its component models. Well, it captures them, but it doesn't capture the differences in magnitude and distance scale. So, right, yes.
Yeah, scale backbones can only really be moving horizontally in this picture here. So when you asked about the other direction, in essence, probably one sort of direction here is magnitude scaling differences, and one direction again might be more distance scaling differences. But then if it's more than just if it's a break in the scaling, it would have to be even a different sort of bend or something like that. So it's not as simple as saying what's going on. At least the x-axis, that was mainly the constant scaling, is the way to think about this. And part of this is if you pull out a case, can we have one where it was a 1.3 versus a 1.0? Do we know for the geometrical spreading? If we go back to that one, so what's the 1.3 model?
I think these ones are
AB14, so that's sort of, and then there's the 1.0 model going let's not do magnitude 8, let's do magnitude 6.
What was the other one?
Okay, so there's two 1.3 models, and then Frankel's, and Frankel's is are the -1 model. Right, okay, so actually those two, the yellow and the green, are two good ones to compare because they're very similar except for the slope. So if you compare YA14 and Frankel.
YA14 is here, Frankel is over there, and then we have the AB14 down there.
So if you look at the direction moving from Frankel towards AB14 is the direction you're going to get YA14. So there are sort of road maps on there, and his point is the road map directions other than the constant is going to shift depending on the starting rules, right? So it's like someone gives you a map and sometimes they rotate it on you and they don't tell you it, right?
That's why it is hard to interpret these things. It's in the
Could you put some like basic direction? I know that it can change every time you generate it, but for one specific map, when you find out like that this is distance, can you make like a dashed line that this is distance, scaling direction, this is the S30, so on? Because it'll help a lot.
So this is already what we saw in the comparison with the Yenier and the Frankel model. This direction, mainly difference in slope. And then we have here, it's a difference in slope, but it's the difference is more to the larger distances. So that's the Hassani and Atkinson on the SSHAC data. And now we are comparing cluster 2. So that's the 95th, 5th percentile median, Atkinson prime, and SDCS. And they're aligning perfectly, so it's just mainly scaling them up and down. That's the map for 100 Hertz, for 10 Hertz. So now we have the peer models. So the Arkansas, Oklahoma models are generally lower than the models for the rest, and we can see that. And we also see that the Graves and Pitaka model is slightly lower than the XIM model. And that's consistent with what we observed before. These are the individual EPRI models, and these are the EPRI clusters. Now you can see what I was talking about before. The component models of cluster 2 align in this direction, whereas the 5th and 95th percentile align in this direction. And we'll see that. Yes.
That's just a consequence of...
Yes, that's it. I'm not saying that's wrong, I'm just saying that it's...
It's the consequence of this is Bob Young, the consequence that those two models that were grouped as cluster 2 in some frequencies have quite different behaviors. And they were just being modeled by a single line and a plus or minus that scales them up and down over the whole distance and magnitude range. So ideally, they should have been in, we should have had 5 clusters instead of, but we were trying to make Robin happy.
So again, we're comparing here the model far on the right and the model far on the left, and they're just scaling more or less up and down. Now we compare, that's the Toro et al., and that's the sum of the non-rifted model. So we're going in this direction, and we see how they change in slope. So we see how they cross. We have a change in magnitude scaling and a change in distance scaling. And then same here. Now we have mainly a change as before in the distance scaling for longer distance. And this is the different behavior of the Atkins NOAA 8 and the SDCS model. And that's what we were talking about yesterday. The overall uncertainty is captured by the scaled backbone in this case, but it's not capturing the individual behavior. So it's probably too high. 5 Hertz. Peer models move a little bit in. again, comparing a high model and a low model. We're comparing models that are crossing at some magnitude and distances. And the same here. Well, that's actually good. I mean, it's good to have all these models in there, right? To really capture the difference in all these loads. And now we see more of the, we better see the differences in cluster 2. And we've got the same thing for 1 Hertz. Distances get smaller. Christine?
It looks like the models are more, the new proponent models are more positive than most of the EPRI at 1 Hertz. I mean, it's dramatic. Okay. So the space has shifted. The space that is covered has really been extended to lower, to higher ground motion.
I think we could have seen that. Just go here. And we're going up to here in this case. We're going up to 200 kilometers in this case. So they are a bit more on the higher side, actually. Yes. You need a microphone, actually. I can't hear you. Why? Okay. You're the boss. So that's for 1 Hertz and 19.6.
So this is, again, the different peer models here. There's still only 2 out of a suite, right? There's a lot of different things we haven't considered. We talked about other ways to fit.
We were actually quite happy when we plotted them the first time. That's the difference. Actually, so the difference between these models actually gets a bit smaller for 1 Hertz. They're closer together at 1 Hertz. And we see that also in the map is not going out as far. We have different models. And the last cluster. So those are the Salmons maps for all the models, so for the NGA East models and the EPRI clusters. We can say approximately which models are close together, and what one can do is define clusters based on the model space and say these models all give approximately high ground motion, so if I want to cluster them just based on these 29 models, I'm just going to go with 1 cluster here, 1 down here, 1 up there, and then combine those. One could do that, actually. And it's, well, we only need 1 plot instead of hundreds of plots over here. So that is one of the motivations. Now we're coming to extrapolating the model space. So we have 29 models. In the end, maybe a bit more, maybe a bit less. But 29 models means 29 discrete model predictions. That means 29 discrete points in model space, 29 discrete points on the map. And that's not what we think is going on. We think the epistemic uncertainty should be a continuous distribution. So there should be a continuous distribution over predictions at each magnitude distance pair. And to assess the center, body, and range of this epistemic uncertainty, that should be based on the continuous distribution and not the discrete one. And so one of the solutions, what Norm talked about there yesterday, is the scaled backbone. You just take one model, shift it up and down. But that misses epistemic uncertainty in magnitude and distance scaling. EPRI actually circumvented that because there are 4 clusters, and these 4 clusters have different magnitude and distance scaling. So you have different scaled backbones. Essentially, you have different scaled backbones there. But it's still a question, how should we select clusters, and how many clusters should there be? And in SWUS, it was tried to estimate the distribution of GMPs. And I'll just go in one slide over that. So there were some initial GMPs selected that were assumed to be applicable. There were a different set for the Upper Canyon and a different set for Palo Verde. Each of those were fit to a common form. So basically, that means we reparameterize each GMPE to have the same set of coefficients. Means if we have, and since we have the same set of coefficients, we can then calculate the joint distribution of those coefficients. Once we have the joint distribution, we can just sample from that. And sampling from that distribution means we now have a mutually exclusive and collectively exhaustive set of GMPEs. Then we calculated Salmon's map, where in that case the distance in the high dimensions was based on the weighted Euclidean distance. And that means each distance add a magnitude distance. Each high dimensional distance add a magnitude distance pair was weighted by its de-aggregation weight. And then the map was used to select a manageable number of GMPs. So this is how it looks like in red. We have the original GMPs, and in gray we have the fit. We have samples from the joint distribution. So we have 2,000 models sampled from the joint from a GMP distribution. And they cover a wide range, and they cover a much larger range than the original GMPs, but they also cover the range like in a continuous fashion. That's nice. This is against magnitude on the footwall, and that's against Rx, so over the fault. And then this is the same thing on a Salmon's map. So that's basically taking these points at each magnitude and distance prediction. We had a 100-dimensional, more than 100-dimensional ground motion space, and we projected it down into 2 dimensions. And now the red points are the original GMPEs, and each of those points is one of those sampled models. And they cover different ranges. So again, in this range, we have more or less up and down scaling, and then we have differences in the slope. And now the selection in SWUS was based on these 2,000 points. So from these 2,000 points, some 20 to 30 models were selected. And that was done by carving up the space into a smaller space, saying, we believe this should be the range that should be considered. Everything beyond that is out of the range that is considered applicable, or that's beyond the range of the epistemic uncertainty. And then points were selected on these different ellipses, and they were scaled up and down. So the ellipses were scaled to have a bit more epistemic uncertainty capture. So basically, this one is to capture the range, and these two are to capture the center and body. And then for each of those, some area of influence was selected, and then the weights are based on the areas that those different models occupy. And the reasoning behind that is that the model that is far away from all other models, that means a model that provides very different predictions, gives potentially more information than two models that are really close. So that means if a model is really far away from all the other models, even though it might be considered unlikely, because it's far away, it provides good information about the range. So therefore, it should be given a relatively higher weight. So that's why so these areas are based on the Voronoi diagram. That means based on the closest distances between all the points. And so models that represent a larger area should be given a higher weight. But if they don't fit well, or if they're far away, they're downweighted. So it's a compromise between providing more information and not being applicable.
And you mean far away from the center?
Yes.
Okay.
I'm basically meaning far away from everything else. Yeah. So, but that means. So, for example, we could have. I mean, if we just take this point out, these 2 points out, this one would be farther away from its neighbors. That means it would cover a larger space. It would cover a larger area in ground motion space. So it should be.
So I understand the area. The bigger the cell, given everything else is equal,
Right.
It's going to get a higher weight because we're just discretizing the space, right? I'm not following the further away.
So for example, if you have two models that they give really, really close, really similar predictions, and one model that gives a prediction that's pretty far away. And
Within a cell, or
just
in general?
In general, in an abstract sense. So even though you say, okay, the two models are more applicable to my problem, then you would give them a higher weight. But the two models, because they're close by, because they give very similar predictions, they might be redundant. So if you give both of them 50%, you're basically given that part of the model space, 100, or if you give both of them 45%, you give that part of the model space 90%. On the other hand, the model that's far away covers the range of the uncertainty. So to capture the range, you need to give that model a significant amount of, or not as significant, but you need to give that model some sort of some weight. So that means the farther away the model is, the more potential information it has compared to the other one.
How do you evaluate the size and shape of those polygons, the outer perimeter?
You mean the outer ones? So basically what we did is we added a fourth ellipse and then took the outer points on the third ellipse, which define the range, and then take the same in the same angle on the fourth ellipse, and then calculate the Voronoi diagram. And that gives us these boundaries, the outer boundaries of the cell. And the reason is if we don't do that they would go to infinity. And if we base the weights on the areas, they would get infinite weight.
Essentially saying anything outside those blue cells, we are deeming as zero, right? That even though there are models out there, we don't need to go that far out. So we did create more models want it to, or at least a broader range, which is the goal, right? We want to be sure we get a big enough range to start with, and then we can chop that back. The evaluation is how far out you go on the ellipse. Whether he changed the shape of these, in principle, should not matter to us as long as we have enough, right? So, because he's going to scale them by area, so whether I had 20 or 30 or 40, that's just, how finely do you want to discretize any distribution? John.
John Evans, Geological Survey of Canada. Do you have a target for the number of points that fall outside the captured area? No. Okay.
You mean outside here? The number of points here? No. No.
All right, Christine. Those models are generated assuming equal weight to all of the candidate models starting. Okay, so if you believed equal weight was right, then you would say, wherever they're more dense, they're higher weight, and you could have just used that as a way to do it. And then what you suggested makes sense. Okay, we want to go out to get 95% of it or 99 or whatever. But we're going to override that equal weighting. So some other information now needs to come to play on the problem. And we haven't shown it here, but in Swiss we then use alternative data sets to help us, or with mean residuals. And if I've got 100 observations, how much am I going to say I could be off? My mean could be 30% low or 50% low, or what are my constraints given sets of data? And then we can look at alternative sets. So that's what's really controlling this. We think the data here are adequate, that our mean residual from these observations shouldn't be more than, let's say, plus or minus 0.3 or something like that overall. Now, that will still change a lot at a given MNR, right? Because this is the residual for the mean of your whole data set. So when we have a lot of data, I think I ought to be getting the mean about right. Okay? But I might be off close in at large magnitudes and so forth. But where the data are centered, which is kind of what this is getting, I shouldn't be too far off of that center unless I think my data is not applicable. Then you make the same map with a different set of data or set of observations or whatever it's going to be. So that's what's trying to limit the map. But as long as that outer area is big enough, then we're happy because we can say I've got a bunch that I didn't miss anything, and I can start my evaluation to pare it back down. Is that making sense, John?
No, fine.
Right. So basically, the selection of the range was based on the comparison to data. So the range was based, for each of the models, residuals and the likelihood was calculated to a subset of the NGA data set, to the European data set, to, well, in this case not for the simulations, but for Diablo Canyon also was compared to simulations. And then it was said, okay, every model that has a residual that's larger, or whose absolute residual is larger than 0.3 is considered not applicable. So that's kind of defines the range. And then in this direction, and the range is in that direction, is trying to capture the original GMPEs and going a bit further out. That was basically the main rationale behind selecting the models. And then, well, that's how the range, so the ellipses define the range, and that's how those were calculated. And then the individual selection was based on where they coincide with those contours.
I think the real advantage of this is the evaluation phase becomes more structured and actually easier. Okay, instead of saying which model is better than the other models, you can start to say what are the limits that the data tell me my models should cover on, let's say, a mean residual, mean misfit from a lot of data points. So let's say if we're looking at the eastern U.S., I shouldn't be really far off when I'm looking at magnitude 5 at 200 or 100 kilometers or something. But we also make sure that it's at least as big as the range of the candidate GMPEs, because we let them all through, right? So we want to go broader than what that is. So he had that point we did in this particular case, plus or minus 0.3 in a mean residual, or further out than the smallest, than any of them GMPEs, plus epistemic uncertainty that was added to them, so it was broadened out. But it gives you an easier structure for the way you do the evaluation. I found this was a much easier way to do the problem than when we sat there before going, well, this one had more data, or this one had a quadratic magnitude term, so we get twice the weight of something else, and so forth.
Okay. I can sort of see the rationale behind limiting the range of your ellipse for Diablo Canyon, because there's a lot more data that's applicable to Diablo Canyon tectonic environment. But for central eastern U.S., all of your data is less than 5. Well, not all. Most of your data is less than 5.5. So do you think you can extrapolate the mean residuals for magnitude less than 5.5 and all the way and assume that the same residual or the same could apply to high magnitude?
I don't think so. Maybe the TI team has a different idea, but no, I don't think so. I think in the East it would have to be a subjective decision. But
so there are numerous ways we highlighted that we think we may use. So instead of, we're going to look at the data where we have it. We can use simulations in the background as a reality check. Either the point source or the finite fault. It's not good for absolute values, but these are different tools we can use, but it's going to rely more on judgment. And we don't have this data-driven factor. Beyond 5, that's where the magnitude scaling makes a big difference, and we have no way to really test it. So, but we could, yeah, go.
You can still limit the range by the range of published models, right? Because already we are extrapolating beyond the range, because this is an interpolation process and an extrapolation process. Now, how far do you go out then becomes an issue. Do we take the biggest and smallest models in this space here and go out another factor or whatever that's going to be? Once we put the units on there, then we'll be able to know what that range means. I think that's going to actually help a lot. But at some point we have to restrict it, because he's going to be generating models that go too far out, or at least that's the expectation. But it's not as easy as the cases where we had in California, where we had a lot more data. So where we use maybe plus or minus 0.3, you might need plus or minus 1, right, in the East or something like that, a much broader range. And those ranges of the GMPEs were already capturing a factor of 4 or more, right? Just from, it looked like a small range on Nico's plots, but it's a big number. C1 and C2 on the 2 axes?
Coordinate 1 and coordinate 2.
So if he would, so this is the standard error of the difference between the GMPEs times n is the problem, right? Because he has n number of points, or times root n, right? So if we normalized it, then those axes would actually be the standard deviation of the difference in the ground motion predictions as measured across those MR pairs. And now you could attach a real number to that, right?
Actually,
actually in this case we would need to normalize by something else, because that's the weighted distance. But
also, going back to the units, I was thinking, because this transformation is nonlinear, it may be true, it may not be true that you keep the same units as your original distances.
The whole point is the distance on this map is proportional to the distance in the high dimension space.
Is the closest possible approximation you can get.
That's good enough.
That's good enough.
Yeah.
But it could be that you have a huge distortion.
But that's, if it's a huge distortion, then this isn't working.
Well, if you're paying a price, going to 2 dimensions, from 20 dimensions to 2.
It would still work. I mean, what we're always thinking about, and if we're like sampling, then it's almost linear. But you could have a curved shape in your high-dimensional model space, and you can still plot their ways, and this can approximate it to plot curved shapes onto 2 dimensions to project that down. I mean, that's basically what a map is, like normal map. Which works fine on small scale.
So it gets distorted from one end to the other.
Yeah. When I go from Berlin to San Francisco, and I go the shortest distance on the map, that's not the shortest distance in 3 dimensions. And that might be, if we go to very large distances on the map, that might be the case. But locally, I mean, the assumption is that locally it's flat.
Yeah, that's what we heard.
We're making progress.
I had a question to start. So you're doing this at the separate periods, right? So does that mean you're essentially using different ground motion models for different periods? Or
Yes.
Is that something we want to do? When you're making a uniform hazard spectrum at different periods, do you really want that to be formed from different ground motion models at different periods?
The short answer is yes, and we thought about that exact problem. Essentially, what it's trying to do is to say, I can't give a weight to a single ground motion model at all periods and still capture what the range is going to be. And so when we try to do them all at once, it really, the period differences between the models was big enough that we started to not really get to be able to see the magnitude and distance scaling differences.
Yeah, and I think that's sensible, because if you look at where the different ground motion prediction equations come from, most of them probably are better in some period ranges than others. So it's not unreasonable if they end up implicitly getting different weights in different period ranges.
When you do the whole thing at the end, if you compute the mean weighted model at all the different periods and compute a spectrum, it's actually pretty smooth. It's a little jagged, but you could, if you chose, you could end up smoothing that. So you can end up creating, here is the single representative model, if that's really what you want.
Yeah, and a good example of the different weightings would be, for example, a stochastic point source model you might think deserved a good weight at high frequencies, whereas it deserved a lower weight at long periods. At long periods, you would want to give more weight to the hybrid broadband methods.
So a model might be in a very different location away from the center in these maps based on one period versus the other, I think. But we did think about that, Art. It actually started in that direction, saying, can we just get, in one of these points, choose the model that works at all periods best? And
well, basically, so, I mean, we tried to rotate that in the beginning, to rotate the maps that they, for each period, roughly are comparable. And then I just, when I selected the model that was the same distance and in the same angle over the different frequencies, it provided a relatively smooth spectrum. It was wasn't completely smooth, but it was relatively smooth. So we cannot, it loses all physicality, but is that worse?
Yeah. But I think part of what we said is 2 years down the line, maybe we'll try to solve that problem. But that's not key for what we're trying to do here to capture the ground motion models at different periods. He said we could do it by subsets, and with our schedule, I think the answer is no. We just got to go forward and get out sets of models, but in the end, we need to show that the mean model, when computed over all periods, it has a good shape to it. Otherwise, something went wrong.
I got you.
The fact that we're using ellipses, does it mean that we're...
Hold this like...
Yeah, I don't really know what I'm trying to say, but which is part of the problem. Are we assuming a symmetric distribution about the model space when actually it could be skewed?
Yes. Yes.
And is that a problem that we need to evaluate in some way, or we just say it's symmetric and move on?
No, because go to your cells. Can you just show one of those? Here, we don't have to have symmetric weights at all. In fact, they don't need to be weighted highest in the middle. The middle is just where most of the models are piling up.
But those cells are still created out of the ellipses, right?
Yeah, but
right.
I don't...
And those ellipses are generated from the symmetric.
But I don't care as long as the space that I'm sampling from that... Take any distribution you've got, or even, let's say, a log normal distribution. I could say, well, I'm just going to move, every 5 units, whatever it is, and sample it. I don't care. I can adjust that by what the weights are going to be, because the weights aren't equal by any means in these cells, right? They're related. And I could have divided this into 1,000 points, and then I have really, just a very fine sampling, or I could have made it 10. But the asymmetry will come in the weight.
Okay, and then how do we, Gabe sort of mentioned this, is we have this high dimensional space that how do we truth it out and make sure that we're not doing something really bizarre?
We run the hazard for the original GMPEs as published compared to the hazard runs from our selected ones here, and they better make sense. Right? So that we ought to be reproducing that.
Also, isn't there or was that only for PCA? Wasn't there a metric that would tell you how much of the variation you were capturing?
So that would only tell, in PCA, it will only tell you how much variation you capture on the map.
But so with PCA, okay, on the map, that's right, not in hazard space.
No.
But also, is that applicable to SAMOS or only to PCA?
That's only to PCA, because that's then in PCA, then actually the coordinates do have a meaning, so it's corresponding to the principal component. And but here, and then you can judge the fit based on the amount of variance that you explained.
Our fundamental assumption, and then get to Art, is that if we carve up this space, we are discretizing all possible models. That's really the key thing. And if there was if there's something that's fundamentally missing from this, then we would be in trouble.
I might have missed this, but when you're generating these models, you're fitting the equations and you're varying these coefficients.
Yes.
Now, I'd feel a lot better if you were sort of varying physical parameters like Q or geometrical spreading and that kind of thing, and then refitting the curves. That kind of thing. Because I don't know what changing the coefficients really means physically sometimes.
Yeah.
But we have all of those models to work with, so we know how there's a correlation with the coefficients are. We're trying to fill in between the models.
Yeah, just on Art's point there, you could actually do that with our model, with EMRA's model, because it's parameterized in terms of stress and attenuation coefficients. So you could put like a distribution on the stress and all of those other coefficients and generate a bunch of models that way.
But also, Nico, you're going through and removing non-physical models.
Yes.
So if a sampled model came out with essentially negative Q or positive gamma term, then you're dropping it out.
Yes.
So the models that get sampled have some check on them that they at least should behave how we expect them to behave physically.
Yeah, so the first step is the pass, no pass. Then they go in the map, but keep
No,
in mind...
the sampled model.
The sampled, yes, that's what I'm talking about before that, before we sample them.
No.
Pass, no pass.
No, I'm talking about the generated model.
Okay, the generated, yes. But, so the key, I think, is that all those models are reparameterized into a common functional form that could be simple enough. It might not be exactly Q, but just the R term at large distances and those scaling things, because we don't retain the functional form. At least for Swift, it was not retained. For these, you want to talk?
Basically, so I've done that a while ago, but I've done that running a lot of stochastic simulations, varying stress parameter, varying Q, varying kappa, and then basically doing the same thing, putting them on the map, and then you can actually see how models with high Q are in one direction, models with high kappa are in the other directions, and so on and so on. So you can do that. That's basically, and you can, if
that might be
simulation has been done.
What Gail had talked about, sort of the road signs you put on here, could be done with that model, right? To say, here we've changed it, and it's moving this way. Because we're trying to not just get one type of model put in here, but bringing in the empirical models and the simulations and so forth. And how do you throw them all together and evaluate them? But mapping out directions in particular and what makes sense, you would be able to do that just with the parametric variation of that type of a model. That's what Nico had done before.
I think we need to move on. It's almost coffee time. And so basically, that's the same map. Are we going back to comparing to the data? That's the same map as before, but it's the likelihood. And so we're not only comparing the models to residuals, we're only calculating likelihood, and then models with higher likelihood, but the data has higher likelihood, they are by definition more likely, so they will get a higher weight. That's another way to compare against the data. So then in total, selection and weighting is based on the original GMPs, capturing them on the map, and also in comparison to data. So not selecting models that are not supported by the data. So basically, it's capturing the range of the original GMPs, capturing a little bit more, but not capturing too much. And then
Nico, I missed the first point. I thought that original GMPs are gone by the time that you generate all the space.
Yes,
and
but it's still in the selection process. I mean, so when we go back, we don't want to select the space over here. Yeah. We could do that if you have reason to believe that that's where you are, but so we wanted to capture the original GMPs, but
and they're not gone, you said.
No,
they're there.
They're in there.
They're in a cell. You could choose them if they are a reasonable representation of the.
They are 19 out of 2,000.
Correct.
Yeah.
Right.
And then the space that was selected is partitioned into cells, and then the weights are based on the area of those cells and some statistic inside those cells. So that means if all the models in a cell have a high likelihood, that cell gets a high weight. If they have a low likelihood, that cell gets a low weight. And then in each cell to be more close in hazard space, the model that is closest to the mean hazard curve of all the models in that cell. So there, for example, if we go back in this, there might be 50 or 100 models in that cell. For each of them, a hazard curve was run with a simplified source model, and then we calculate the mean of the hazard of all those hazard curves, and then we select the model which is closest to that mean. Because models that are far away or relatively far away in ground motion space can still be very close in hazard space if they are close at the relevant scenarios. Yes.
John Adams, Geological Survey of Canada. That presupposes the hazard value that you want, in other words, probability. Because if you choose different probability, if it's a very high probability, it's likely to be dominated by small earthquakes, and some models will do better than others.
Overall.
Yeah, an example of that would be if your goal was hazard mapping, 500 years or 2,500 years, your weighting may be quite different from
yes.
GMRS type at 10⁻⁵.
Might not be the best way to do it in the East, but that was a good way to do it for site-specific PSHA.
Am I hearing that this set of ground motion model is developed specifically for, it's developed for site-specific study?
No. Go ahead.
He was just referring to when it was done for Swiss, it was for site-specific.
Right.
So then the disaggregation, all that rolls into the hazard curve, and it's consistent. Might not be applicable for the East to do that.
But again, the question between the 500 and the 10,000 years still remains.
Yeah, we can.
You could get different emphasis, different ways.
Yes.
But I guess that's the bottom line.
Yeah. Or you can look at it. Yeah.
So maybe I should get some clarification. Can you go back to the previous slide? So on the fourth bullet, model is selected based on hazard.
I should have put us in, this is what was done for Swiss.
But we can run a even representative hazard if you have, because we can take several sites. The hazard in the East is, there's a host zone and there's a distant large magnitude source for most sites. And you can capture that kind of behavior just to make sure we are doing that. You could even do it for 5 different sites and average it and say which one gives the closest to those 5 or something like that.
Okay. Well, I'm not familiar with the hazard.
The magic 7, right? You could use those. It's just some way to check what's happening in, you're already picking a model out of that cell, right? So you know you've got a model that represents that part of the salmon's map. But in the cell I might have 500 models. Which one of those 500 would I choose? I'd rather choose one instead of a mean ground motion. We want to have something that is mean in terms of its impact on hazard. So you need a representative, simplified source model that could be used to do that step. It's not the site-specific hazard. Even in Swiss, it wasn't the site-specific hazard. It was overly simplified so that we would broaden out a little bit the contribution and we weren't gearing it right towards the exact, single source that was controlling the hazard.
So I guess, okay. So you're saying that one set of GMPE selected for a given site, you can use it for another site that is hundreds of kilometers away?
We will say the set of GMPEs from this model will be generic for the Eastern United States. And the hazard calculation that we use there will be a representative hazard for a generic site in the east.
To be honest, I think the best way to do it would just be, this is my mean, this is my covariance, and you figure it out for your application.
Good luck. Yeah, one question for clarification, I guess, unless you haven't answered, Brian, yet. Now, the hazard weight is used only to choose a point within each cell.
Yes.
It is not used cell to cell.
No.
Okay.
No, just within the cell.
All right. So it's in many ways a very limited use. To the extent that the cells are small, it's a limited use.
So I just did, I'm not going to do that because I think we don't have time, but I did something non-model based. I just sampled 1,000 new models from a subset of the proponent models, and that's how that looks like. There's no model in there, just mean and covariance of the ground motion predictions of those variables, and it works pretty well. So you can just do that. You can just calculate the mean of all GMPEs, calculate the covariance of all GMPEs, and then you can generate thousands and thousands of correlated new ground motion values. And because they are correlated, so because we have the covariance structure, they actually look pretty physical. So there's nothing going on that's really bad. So that's just we don't have time, but that's just generally the correlation between a ground motion at magnitude 5 and a ground motion at magnitude 6 is captured by the functional form. But you could also capture that by a covariance. And that's what I did here, and it worked pretty well. And that's how the map looks like based on the seed model. But there's no time to do that. But I could use the covariance structure to extrapolate the GMP. Yes. Yes. The question was whether this plot was for the east. Good. So basically what I did here is I had the covariance structure between all my 28 ground motion predictions. So the covariance structure, so I have a 28-dimensional ground motion vector, and I have a covariance matrix, which tells me how the ground motion at magnitude 5 and the ground motion at magnitude 6 are correlated. And then I actually used one of Dave's models, which I said, okay, I only know this up to magnitude 7, but when I have the predictions of up to magnitude 7 and I have the covariance and I have a multivariate normal distribution, I can condition on the values that I have and then get the conditional distribution at magnitude 8. And this is what's shown here. So that's the thick black dot is the actual value at magnitude 8, and that's the extrapolated value. When I just assume that ground motions at magnitude 8 are correlated with all the other ground motions. It works actually pretty well, but there's no physics behind that whatsoever. But it also works when you go from 500 to 1,000 kilometers. And that's it. We can look at the hazard curves from 1 to 1,000 kilometers if you want, but no.
Thank you so much. Well, okay, quick question, one.
Yeah, the quick question is, when we saw the developers present their models, they generally excluded the Gulf Coast. Would you have to repeat this for the Gulf Coast? Or how do you account for the Gulf Coast?
It's not in there.
If we have different models for the Gulf Coast, we would have to repeat that for the Gulf Coast.
Thank you.
Okay, we're taking a break. let's try start at 3:15. Huh? Huh? I will try at 3:15, so I know that 3:20 will. That's fine. Okay, everyone. This is the last stretch. Come on down. We're almost done. So everyone, this is the most exciting part of the meeting. So, yes, this one, these types of plots have units on them. Dave Bohr, Bob Young, Albert. Yes. Oh, give it to myself. He's going to package it. Computer died. Ooh. That is scary. It's coming back. Okay. Okay, so the PDF, right? We can try it. Why don't... equation? No both is voluntary? No both structures? Yes, thank you. Some of them are that? Okay, so let's go with the PDF. Yeah, let's go safe. Okay, so the last section or session for today is Linda gonna woman this whole discussion on the sigma. Okay.
Good afternoon. So we will start now the Sigma Marathon. I have 3 talks back to back. So I work with the Sigma working group, and our goal is to develop models for tau, phi, and PSS. So I'd like to acknowledge all the interaction and feedback from the other members of the working group. So the outline is basically the 3 presentations that are on the schedule. So first, I'll go through the general TI team approach for the Sigma Logic Tree, give some background, objectives, and general approach. Then I'll go through the preliminary results of the analysis of the SINA data.
I'm going to help you with the presentation.
Oh, okay, sorry.
I'm going to get out of your way. Yeah.
Okay, great. And then finally, I will talk about the preliminary candidate Sigma models, the new and also some of the existing models. So the objective then is to develop models for tau between event standard deviation, phi, ergodic within event standard deviation, and PSS, the single station within event standard deviation, that would apply for the east for M4 to 8.2 distance up to 1,000 kilometers. The general approach is to look at the SINA data and analyze the residuals with respect to a developed GMPE for PSA, evaluate any trends there. And as we know by now, we are data poor in the large magnitude range especially, so we would compare SINA, phi, PSS, and tau to other existing models in the common or overlapping data range to inform the extrapolation of the SINA models to larger magnitudes. And then finally, we develop new models and evaluate existing ones. So I'll start with this usual slide that I'm sure probably all of you by now have seen many times. So this is delta ES is the total residual, the misfit between the observed ground motion and the predicted one for earthquake E recorded at site or station S. This can be divided into 2 components, the between event residual, delta BE for earthquake E, which is the average misfit of the observed ground motion for this particular earthquake from the median prediction. And then the remaining is the delta W ES, which is the within event residual at station S for earthquake E. And this is the misfit between the ground motion cannot get the mouse? It is? Oh, I don't see it here. That's weird. Okay, but for the one single recording for this earthquake from the earthquake-corrected median ground motion. So the standard deviations are then tau for the between-event residuals and phi for the within-event residuals. Sigma is square root of tau squared plus phi squared. So then this is for the ergodic phi. We can move into the single station phi if we have multiple recordings of ground motion at individual sites. That would allow us to estimate the systematic site effects. We call them delta S to S with a subscript of S to signify a particular station. And we can remove these systematic site effects from the ground motion variability. By doing this, we can estimate single station phi. So then delta S to S is the systematic deviation of the observed amplification at a particular site from the median amplification predicted by the model. So in a simple way, delta S to S would be the average of the within-event residuals at a particular station. We correct the within-event residuals to remove this site term. We can get the single station within event residuals. Their standard deviation is the single station phi. And then we can also look at the site-to-site variability for the site terms. So in summary for this terminology, we have the between-event residual. Its standard deviation is tau. We have the within-event residual, delta WES, with a standard deviation of phi. We have a site-to-site residual or site term, and that's the delta S to S. Its standard deviation is phi S to S. And we have the single station within event standard deviation, delta WS, with a standard deviation of phi SS. And when we combine phi and tau, we get the ergodic sigma. We combine phi SS and tau, we get the single station sigma. Okay, moving on to the second part of my talk, which is presenting the preliminary results of the CNAD data analysis. So I'll give a description of the data distribution, the GMPE functional form, and some residual plots, and then we'll look at tau and phi SS and phi of the data. So this is the data distribution that we used. Now we're looking at earthquakes that recorded at least 5 recordings, and we do that. We impose this criterion to get a reliable site term. So Justin ran a regression for PSA and used this data set. He also excluded data that had questionable quality. We also excluded duplicate recordings. So what we end up with a total of 3,933 recordings from 65 earthquakes, 746 stations. In blue, these are the tectonic data, and in red, they are the potentially induced earthquakes recordings. As you can see, they make about almost half of the data set, and they come from only 11 earthquakes, but they're very well recorded. This plot here on the right shows the number of earthquakes at the different periods in the data set. So you see how it decreases around 1 second and on because of the low frequency filter. However, one thing to note is that in this stage, we haven't imposed the limitation of the high frequency to the data, and that's something important to remember when we look at the results at short periods. Here, the plot on the left shows the magnitude versus depth of the earthquakes in the data set. In blue, they are the tectonic earthquakes, and red, they're the pi, and you'll see they are shallower. On the right is the histogram of the frequency of stations that have different number of recordings. So you'll see a lot of the stations have less than 3 recordings, which we wouldn't use eventually when we go to the single station fee because that doesn't give us a reliable site term. This is the data distribution split by region. So region 2, which is the path being contained within central US and Canada, is the largest part of the data. Then region 3 is in green, path within the Appalachian, and 4 within the Atlantic coast. There are very few data, and 5 is path crossing in green. In red. So Justin fit the data with this preliminary model for PSA. He took the hinge distance at 50 kilometers, and the model is relatively simple. It's got the magnitude term, the geometrical spreading, the Q, and the site response, linear site response. C6, the fictitious depth, I believe, is based on ASC14. And then C7 distinguishes between the Appalachian and the non-Appalachian Q attenuation. This regression was done for distances up to 1,000 kilometers and does not include the Gulf region. So I'll show a few plots for the residuals. This is the between event residuals at a period of 0.1 second on the left and 1 second on the right. And these are between event residuals versus magnitude. In blue, they're the residuals for the tectonic, and in red for the pi. The lines here show the binned residuals. And one thing that we see is that this trend of the between event residuals versus magnitude for pi. This is for a period of 1 second here. And again, red is the trend that we observe for pi, blue for tectonic, which looks reasonably good. And now these are between event residual plots versus hypocentral depth, and again for 0.01 second on the left and 1 second on the right. And I highlighted again the residuals for pi versus non-pi events. You'll see here that for pi, the average residuals there is an offset, and it's the other way, and it's up at a period of 1 second. Within event residual plots versus distance at a period of 0.1 second on the left and 1 second on the right. So the blue points are for the tectonic data. The red are again the pi. And so the red line shows the average residuals in different distance bins. And one thing we see is this trend for the pi data versus distance at the short period. At the long period, it's no longer there in the same way. Within event residuals versus VS30, and the averages look pretty good at 0.01 second and at 1 second. And I should say that Justin has looked into this regression quite a bit, and there's still work to be done for dealing with the data from the potentially induced events mainly. Okay, this is the within event residuals by region at 0.01 second and 1 second. And blue is region 2 within central US. Pink is where all the paths are crossing, and region 3 is in black for the Appalachian. We don't really see trends except for region 4, but there isn't much data also there. All right. Preliminary results for tau. Justin, if you have something to add on the regression, yeah, okay. All right, so tau. We looked at the between event residuals from this analysis of the SENA data to estimate tau. So on the left, here is a plot of tau versus period using different minimum number of recordings per earthquake in the regression just to evaluate its impact on the results. There isn't a big difference, and I end up using n-min of 5, which I may revise in the future because by the time I get to PSS, I barely have any data left. But for now, we are using n-min of 5, and that gives us 65 earthquakes. On the right is tau versus period for n-min of 5, but imposing different minimum magnitudes to use. So in blue is all the earthquakes, basically, n-min 2, and then this is black, I guess. And then I use n-min 3, 4, and 5. And you see here the number of earthquakes that are left with a different minimum magnitude range imposed. So even though we are interested in magnitude 4 and above, I actually use magnitude 3 to have some earthquakes left. This plot here on the left shows tau versus period, but for the tectonic events versus the pi. So pi is in red. So this is just the standard deviation of the between event residuals for pi, and this in blue is the standard deviation of the residuals for the tectonic events. And you see that there is difference there. Here on the right, so here I use all magnitudes. Here I try imposing the minimum magnitude limit of 3, but that doesn't change the results much. So there seems to be a difference in tau for pi versus tectonic events. This is a comparison of the results for tau that I get for SENA versus 4 NGA West 2 models as they are proposed for application. So I evaluate them as magnitude 4.1, which is the average magnitude for the SENA data set. I have also Zhao in there in red. So for the SENA tau, the black data points are the tau for all earthquakes, and then the open circles are tectonic only. So you see here that tau seems to be smaller based on these results compared to NGA West 2. Then I evaluate the magnitude dependence of tau by binning the between event residuals into different magnitude bins. And so the data points are the tau in the different magnitude bins. The solid points are using all earthquakes. The open are only tectonic. And here I show also the 4 NGA West 2 tau models that are all magnitude dependent, and then the Zhao here. So you'll see the error bars are large and don't have much to go with beyond magnitude 5. So this is at 0.01 second, and this is at 1 second. I looked at the depth dependence for tau, and I am showing here the results for 0.01 second and 1 second. And again, the solid circles are using all earthquakes, and the open ones are for the tectonic only. So basically here they overlap because the pi earthquakes are only here. This is the only place where there is a slight difference. And this is for 1 second. There isn't really much of a trend with depth. All right, moving on to fees. I have to say, are there any questions? Because I'm going through 2 hours. Yes.
I do have a question. So on your 0.01 seconds, so how many data points did you have that were even, because you applied the usable bandwidth?
No. So we did not apply the usable bandwidth on the short period.
Okay.
Which is something that we want to explore, but I am afraid we'll end up with no data.
Because the 100 hertz is kind of extreme given our data. It would be better to... yes.
Linda and I were talking earlier about this. I think an approach will be to build a model up to 10 hertz, and then above 10 hertz, just simply apply that at all the higher frequencies. You don't have an updated check. On the tau, didn't the taus go down at small magnitudes, or was that only at long periods? There was a. I remember in the NGA data, it really came.
Yeah, I removed those plots because I did look at it based on the between event residuals of the NGA West 2, and yes, sometimes it goes down, but then the modelers.
At long periods, I think that's right. It was. So it was. When we built the model, we didn't let it do that, even though the data wanted to.
Yeah. Just.
Linda, can you go back to your period dependence of tau? I thought that the before that, the one you were just on. Yeah, so you're showing pi events have a larger tau in this plot, but then when you go to the depth, it's a smaller tau for pi events. Is that true?
So yes, no, this is a little bit confusing. So
tectonic only. Okay, I understand.
So
Thank
it
you.
brings it up. Yeah. All right. So let's look at the results for phi. So again, here I look at the within event residuals now, and I bin them in different ways, and I look at their standard deviations. So this plot here is just looking at all the residuals at the different periods. So in black is all the earthquakes. In red is the recordings from the pi only, and in blue is the recordings from the tectonic earthquakes. And you'll see here basically the pi makes half of the data set. And there is a big difference between phi for the pi versus the tectonic events. On the right, I have phi in the different regions. So one thing that stands out is region 2, where pretty much all the pi data is. And actually, if you look at region 2, all the data together, it comes out smaller, but that seems like it's mainly because of the pi events here. Otherwise, there won't be a big difference. So
before you go on, I'm sorry, back to tau for a second. Is the data set that Justin gave you for residuals, does it have a depth dependence in it for the source term?
No.
It does not. Okay.
Okay, so here I compare the phi results for SINA, and they are, again, all the data versus tectonic only and pi only, compared to NGA West 2 phi evaluated at magnitude 4.1. And if you look just at this plot, when you throw everything together, things somehow seem nice, but when you look closer, you regret it, and you see that the tectonic are higher, but then you look even closer and you regret even more when you look at distances up to 350 kilometers. And here you see that for SINA, the phi goes up significantly when you limit the distance range to 350. And here I am comparing the residuals of the NGA West 2 just taking the within event residuals and computing their standard deviation. So this is not as proposed by the modelers. So yeah, when you compare here, if we are only going to look at the tectonic events and only within distance up to 350 kilometers, things look much higher in the east. But there are a few things going on. One thing is that there are site classification issues, and then there is this low frequency bandwidth limitation that we did not consider here, and that could be causing
high frequency.
Yes, high frequency. I'm thinking period and frequency at the same time. So yeah, but at 0.1 and higher, things agree more or less.
Another factor, Linda, that may be contributing to a high piece is you're going up to 350 kilometers. So you're probably going to have Q effects. You're going to have small bounces at different distances.
So you think I should look closer?
If you have enough data, I
don't.
suggest you look closer. But because again, except for the long periods, we don't really care what sigma is at 300 kilometers.
Yeah.
And it seems to me this may be contaminated, but on the other hand, if you go to a realistic distance range, then you don't have enough data, or you have to go to very low magnitudes.
Yes, that's the problem. There isn't much to work with. I'll show some numbers of when I look more at the different things. So this is now looking at the magnitude dependence of phi. So again, in black are the phi for the different magnitude bins for the residuals. Solid black is all the data together. Open circles are tectonic only, and then the pi are these stars. And these are the NGA West 2 phi, and they're all magnitude dependent. And I throw in there Zhao, I don't know why. But anyway, one thing we note here is when you look at the tectonic only, it seems to be a little bit on the high end of the phi range. However, when you look at it in this way with magnitude dependence, things look better than when you look at all the data together, and that's because really this data set is biased to small magnitudes, and it's not really fair to compare it to something derived from larger magnitudes. So this is 0.01 seconds. Over here, I limit the data to a maximum distance of 350 kilometers, and I compare the magnitude dependence for SINA compared to the NGA West 2 models. And once we limit it to shorter distances, phi for SINA starts going up higher than the NGA West 2 models.
One other thing.
Yes.
Just maybe repeating or clarifying. Some of those 0.01 second numbers come from TARA data.
Yes, yes.
So they're not really 0.01.
Yeah. So actually at 1 second, things look a little bit better even when we limit the distance to a maximum of 350 kilometers. There is a better agreement with the NGA West 2 phi. Distance dependence. I plot here distance dependence for SINA, and again distinguishing between the tectonic and the pi events, and going to a distance up to 1,000 kilometers, taking all the magnitudes here, 2 and above, and you clearly see a trend with distance. And here on the right, I compare it to the NGA West 2 phi, but to have a more fair comparison, I limit the magnitude between 3 and 6 for SINA. And one thing, this strong distance dependence here, up to 200 kilometers, is not really observed much in the NGA West 2 data set. Then again, the error bars are also very big. So. This is the distance dependence at 1 second. It kind of goes away to a large part, and there is a better agreement with the NGA West 2 data. in the overlapping magnitude range. I also split the residual into different magnitude and distance bins to try to isolate their impact on phi. So this plot here shows phi for magnitude 3 to 4 versus distance. Then you have magnitude 4 to 5 and 5 to 6. So again, SENA is in black and NGA West 2 are these colored. Once you start looking into these different ranges, because there isn't that much data, you cannot really see much going on. It's just big errors. But if there is one thing we see is this distance dependence for the magnitudes, especially magnitude 3 to 4. This is the same magnitude and distance dependent phi at a period of 1 second. And here there seems to be a little bit better agreement between NGA West 2 and SENA. I plot here the VS30 dependence of phi for a period of 0.01 second and 1 second, and I cannot see a significant trend there. Okay, any questions so far? Okay. Moving on to VSS. So I take the within event residuals and I run the mixed effects regression to take out the side term and calculate my single station within event residuals. So to get a reliable side term, I impose a minimum of 5 recordings per station, which I may want to relax a little bit in the next revision. That leaves me with about 3,000 recordings. Just about half of them are tectonic, 65 earthquakes, and 337 stations. This is the magnitude versus distance plot for tectonic in blue and pi in red. And this is the frequency of stations in different VS30 bins. So it appears that most of the stations have this VS30 assigned to them. All right, so doing this, I have phi. Then when we take out the side term, we get VSS, which is in blue. And the side-to-side variability, VS to S, is in red. So you see the decrease in the within event standard deviation when we go to the single station, when you apply the single station assumption. So now on the right, well, this is the left. On the left, we look at these VSS values, but now I look at tectonic only versus pi only versus all the data set. And even here, there is a difference in the VSS between pi and tectonic. So it seems that it's not just a site-specific issue, because if it was, it would have gone out with after removing the side term. This plot here shows VSS for the different regions, and again, as we saw for phi, there is a difference for region 2, but then when you split it up into tectonic and pi, you immediately see that this is because of the all the pi data are in region 2, so they're bringing it down. I had analyzed before the residuals from all NGA West 2 data, but here I show only for ASC14 for VSS. And this is a comparison of the VSS for ASC14 in pink versus SENA in black. And here I am only comparing in the overlapping magnitude distance range, which is M3 to 6 and distance up to 350 kilometers. And again, we see a difference here at short period, and this is a little bit confusing because other studies have found VSS to be stable across regions. So there are some things going on, and it could be the data quality at short periods, but yeah. Magnitude dependent of PSS for CINA. So here, this is both these plots are for a period of 0.01 second. Here, taking all the data together, all the distances, and here limiting the distance up to 350 kilometers and comparing with the ASC14 PSS binned by magnitude. So it seems like for the tectonic PSS, it seems to be higher at a period of 0.01 second compared to the NGA West 2. This is the same slide, but for a period of 1 second. And here, when we compare with the ASC14 PSS, it seems to be in a better agreement at the longer period. Distance dependence. So I bin the single station residuals into distance bins, and I look at PSS, the trend versus distance. And this is in pink, the ASC14. And it seems to be, there is a stronger distance dependence for CINA compared to NGA West 2 up to 200 kilometers. Then it flattens out. This is looking at a magnitude 3 to 5, but then 3 to 6, and it's the same magnitude range for the two data sets. Then I limited it to 3 to 5 because this is where most of the data is for CINA, but then again you see difference. You see a stronger distance dependence for CINA. This is the same kind of a plot for a period of 1 second. Things look a little bit in better agreement at longer periods. I also split the residuals in different magnitude and distance bins to try to see if I can see anything. And mostly the error bars are too large when you start looking really closely. All these plots are for a period of 0.01 second, magnitude 3 to 4 here, 4 to 5, 5 to 6. The only place where we can really compare is right here. This is the same magnitude distance dependence of PSS at a period of 1 second. All right, so we tried to see what is the reason for the pi events having different, having significantly smaller, not just phi, but also PSS. And one thing we tried to evaluate is whether there are path effects, similarity of path for the pi that's making the standard deviation smaller, the PSS to be smaller. So one thing we looked at is the closeness index, which is a parameter that measures the similarity of path. So if you have one station that recorded multiple earthquakes here, and you look at two paths, let's say this one and this one, you can compute this closeness index measure at this station for these two earthquakes, and that will be the separation distance between the hypocenters of the earthquakes divided by the distances, the average of the two distances. And so by doing that, you can look at how similar different paths are. So if two earthquakes are co-located, then your closeness index would be 0. And if they are located in exactly opposite directions, then the closeness index would be 2. So what we did is, to evaluate how similar are these paths, is we looked at expected closeness index for just randomly located earthquakes with respect to one station. Then we compared this closeness index to the average closeness index that we have for the pi earthquakes, and we see how they are relative to each other. So for randomly located earthquakes, a while back I did this simple exercise of generating randomly located earthquakes in a circular area of a certain radius around a station, and I calculate the closeness index of each pair of earthquakes at the station. Then I calculate the mean, and I vary the number of earthquakes and the radius to see how it varies, and it comes out that the closeness index for randomly located earthquakes is about 1.38. So then I went to the data for the pi, and I calculated the closeness index. All that we care about really in this plot is the closeness index. So I did it for pi only in region 2 and for tectonic only in region 2 also, and it comes out to have an average of 1.14 for tectonic versus 0.55 for pi, and that's compared to 1.38 for random. So it seems that there is path similarities for the pi, but I don't know that this would explain everything.
What distance ranges did you consider for that?
Everything. So I probably need to look into closer distances and see.
Yeah, so when you've been by, in general, when we looked at the residuals, the within event residuals, when it was large trends for the pi, it was really within 100 kilometers. And did you see the same thing with the CSS? I don't recall.
I saw a difference everywhere. When I looked at shorter distances and when I looked at all the data.
Oh, those are big differences.
Yeah.
Okay.
Yeah.
Thank you.
Then I also looked at the average closeness index for region 3, and we don't have a lot. This is region 3 here. We don't have a lot of data there, but the average comes out to 1.13. For region 5, which was a little bit surprising to me, the average came out as 0.85 because I expected the path there to be even more different. But I think maybe what could be going on is they're all at really long distances, so they're making the CI small. So I need to look more into that. Okay, another thing that has been done in the Lin et al. Paper there, they looked at the residuals for the Taiwan data, and they said, okay, the residuals are correlated, so they can be modeled with a semi-variogram. So what they do is they take this number here, this delta, which is the difference in the single station within event residuals, normalized. They bin it into different closeness index bins, and they look at what they get, and they can estimate the single, basically, they can estimate the path effects using this semi-variogram. So what they get in their analysis is this nice model here in blue. So I repeated the same approach for the SINA data, all the data, I bin them, and what I get is these data points here. The green is just to show where the closeness index for randomly located earthquakes would be, just as a reference, and the red is the mean of all the data for SINA. And so this is done at 0.01 second and at 1 second. And this looks not too bad. I think that maybe eventually we can try to evaluate these path effects based on the closeness index for the data. And then maybe correct the pi and see if we can use them.
Why don't you point out where the pi number is? You said it was point.
Pi is 0.055 over here.
So that's only about a 10%
yes,
effect on the
I don't think it will solve all my problems, but yeah.
It's in the right direction.
Yes. So what I end up doing now from here on, I will try to build models based on the SINA data, and at this point I just ignored all the pi data because they are so different. But then again, it's not an easy decision to make because we don't have data. So, all right, so let's talk about the candidate models for tau, phi, and PSS. So I'll show some preliminary ones, very preliminary, using this data analysis, and also compare with some existing models. So for tau, we have some preliminary new models using the tectonic SINA data. So we have a magnitude, we can have, one option is to have a magnitude independent SINA model, and remember we only have really magnitudes 3 to 5, so it could be magnitude independent, but then again we need to consider whether it would be applicable to large magnitudes. And the other model is a magnitude dependent model, and the question becomes how do we extrapolate where we don't have data. Then another class is the existing tau models, and even though there are a lot of tau models, at this point here I'm only showing things that have been applied to the east, and so we have the EPRI 2013 tau, which is basically the average of the 4 NGA West 2 tau increased by 0.03. So for the constant SINA model, this is the tau versus period. In black is looking at magnitude 3 and above, and in red looking at magnitude 4 and above. And because I only have 21 earthquakes, if I go with a minimum magnitude of 4, I used minimum magnitude of 3. So then I have these data points. So I chose one constant model, magnitude independent model that is also constant versus period. The other one was to preserve this period dependence in the data, and I get this other option here. And I compare with the 4 NGA West 2 models that are the proposed models for applications, and there's a big difference there.
Just one comment, Linda. So the tau bump is occurring at the same frequency.
I'm sorry, say that again.
Tau bump, the high frequency bump.
Actually, it seems to be shifted a little bit to shorter periods.
Which is
if
what
you
you
really
expect.
look closely, yeah.
Barely.
Yeah, a little bit.
I wonder, are you expected to shift a lot more if it is a kappa issue? That's true. If the data had signal at 100 hertz, but it doesn't.
Yeah.
So this is more the TA effect.
Yeah.
Yeah. One related question, Linda. Was Justin's regression done, say his numbers for 100 hertz, or for 100 hertz? Did they use the same data that you used, or did he use the data?
No, the same.
Okay, same.
Yeah.
Okay.
Yeah, what I showed here is exactly as he has done it. Okay, now we move on to the second.
Just to clarify for a second, so this is a model that was regressed separately for PSA. This is not the FAS through RVD through all that, because she needed to work before we got the model to work.
We should make
to
that
clarify.
clear. Yeah. Yeah, Justin had Fourier model and a PSA model. This is just
all
PSA. Yeah, and different things were done, for both. Yeah. Okay, so then the next type of model that I try to fit is magnitude dependent. So I plotted the data here for tectonic, and then I have the NGA West 2 here. So I have a problem, which is I can only look up to here, and even then, it's not big error bar. So what I did is I said, okay, up to a magnitude of 4.5, I'm going to average all this, and then for larger magnitude, I proposed two options. One is simply following the slope here of CB14, which is in pink, and taking that to magnitude 5.5 and then a constant. The other one is saying I'm going to say that tau at magnitude 5.5 and above for east and west is the same, so I took it the same as CB14. And of course, probably a better way would be to look at the averages of the NGA West 2 later, but for now I just chose one. Sorry, this is 0.01 second here and 0.1 second, so you'll see this is the average, this is one possible extrapolation, and this dotted one is another possible extrapolation to meet CB14 at magnitude 5.5. These are periods of 0.5 seconds and 1 second. So now another type of candidate model is the EPRI 2013 tau model, which, as I said, is based on NGA West 2 increased by average of NGA West 2 increased by 0.03, and so it's magnitude dependent. And you see here their tau for magnitude 5, 6, and 7. And if I add these very preliminary models that I fit, the black ones are the constant. I have to say magnitude independent. One of them is period independent, and one of them is period dependent. The red and the green are at So the red is at larger magnitudes and the green is at magnitude 5.5. And the two options for each color is basically based on the different large magnitude extrapolation.
So the dependence on period is going the opposite way from the western U.S. The dependence of tau on period.
Yes. Yeah.
Why that black line looks pretty good.
Yeah, I know.
So the EPRI was based on preliminary NGA West too.
Oh,
so
yes, before the final
Before
numbers.
the final model.
Yeah.
I don't even know exactly. It may have some differences, the final model's out of 10 seconds. I can't remember that much.
Personally, I don't know if that should be considered a candidate model. That was a very preliminary thing we put together at the time. What you feeling, Bob?
Well, it was a candidate at the time. If you were going to use a model like that, you should go back and use the final, rebuild it from the final NGAs.
Yeah, exactly.
Yeah, I think maybe another existing model that I should add, I mean, this is not a complete list of existing ones. It's just purely the average of NGA West 2.
What, the final one? I don't remember.
The final one,
You should be able to
yes,
see from.
it's right here. These are the final ones, all four of them, so they're not average.
So they don't
right here.
climb as much.
Yeah,
the
they
final
don't
ones don't climb as much. It's long.
Yeah.
I don't know who made the suggestion before I did, but I mean, when you look at the variability of all those things from one NGA West model to another, from one SENA model to another, if you include pi, if you don't include pi, this problem, that problem, that solid black line looks pretty good. Like, really, is there a compelling reason to make it any more complicated than just saying it's 0.3?
Okay. Yeah, I mean, these models are not models that are necessarily going to be used, all of them, or they're for evaluation. So.
My reaction is the same as what Gail's is. We've given this to keep it simpler, but it's worthwhile for you to generate them all, and then we can discard.
Yes, exactly. I don't disagree. I'm just presenting many options that can be thrown out. All right. So for phi, also I looked at deriving some preliminary models using tectonic data, but I decided to limit the distance up to 400 kilometers because of the questionable quality of the larger distances data. But one thing I want to evaluate later on is play a little bit with this 400 kilometers because I don't have a lot of data. So I proposed two models, constant and magnitude dependent, with dealing with the issue of the extrapolation to large magnitude. And I look at the existing phi models for EPRI, which is again the average of the NGA West 2 phi values, but in their preliminary version of NGA West 2, not necessarily the final ones. So this is the constant. So in deriving this constant phi model, which is constant means magnitude independent, I looked at different magnitude distance ranges. So I looked at a minimum magnitude of 3, all the distances, minimum magnitude of 3, 400 kilometers, which is in blue, minimum magnitude of 4, up to 1,000 kilometers, or up to 400. And you'll see here the number of recordings that I have left with each of these criteria. And I decided for now to use minimum magnitude of 3 with a distance of 400 kilometers to give me about 651 recordings to work with. But that means I get this constant phi here with this bump. So, yeah. So then if I take these data that come out for phi with a minimum magnitude of 3, maximum distance 400 kilometers, I can say, okay, I can more or less fit this model to it. And you'll see here a comparison with the NGA West 2 models at magnitude 4.1. They're not too bad at periods, between greater than 0.1 second, and they're very different here at short period. And like I said before, there are at least a couple of things going on, site issues and the reliability of the data at short periods for the TAI array, which is, I think, is more than half of the data. So, yeah. Magnitude-dependent model, I follow the same approach as I did for tau. I binned my CINA residuals here, and again, this is using a maximum distance of 400 kilometers. I drew a constant for the short magnitude. For the large magnitude, I said I'm going to extrapolate in two ways. I will either follow the slope of BSSA 14 for magnitude greater than 4.5 and make it constant beyond 5.5, or I will say that at magnitude 5.5 or larger, the phi should be the same as in the West. And again, a probably better way would be to use the average of the 4 NGA West 2 models. But for now, I just chose here BSSA because, yeah. So this is 4.01 seconds, 4.1 second, 0.5 and 1 second. And when we move to longer periods, things look a little bit in better agreement with NGA West 2. So you'll see here, I follow BSSA more or less entirely. So this is the candidate model from EPRI. It's magnitude dependent at magnitude 5, 6, and 7. And again, it's based on the preliminary version of NGA West 2 phi average. And now I put my phi on top of it. And yeah, I don't know what to say. It's huge. That's all I can say.
But again, a lot of that is this, there's the site problem that we know is a lot bigger, right?
Yes.
And then everything else we're talking about, more variability because of a range of bandwidth in the
yeah,
data.
and the biased magnitude range also. It's really all small magnitudes, trying to be applicable everywhere. I want to say I want to go back and look at the questionable sites and remove them, but I probably will not do that because I'll have nothing to do once I remove them. So I also looked at some existing ergodic sigma models. Some models previous models only gave the total sigma as opposed to the phi and the tau separate. So I compare the EPRI, I compare that to the Atkinson and Adams 2013, which is the sigma for the National Seismic Hazard Maps of Canada. I also throw in there Atkinson and Bohr 2006 and Toro et al. 97. This is what I get for all these existing models. So in black is the Atkinson and Adams 2013. It's constant with magnitude. It changes with period in this way. In blue is the EPRI sigma, again based on early version of NGA West 2. In orange is Toro et al. 97, and the Atkinson and Bohr 2006, which is just a 0.3 log 10 units. I didn't want to put the new model there because, yeah, there's no point there. Yeah. And finally, for PSS, I again looked at deriving some preliminary models using tectonic data with distances less than 400 kilometers. I proposed two models, constant and magnitude dependent. And I look at a bunch of existing PSS models, and the reason why here the list is larger, at least at this preliminary stage, is that it's been observed that PSS is stable from one region to the other. So you could look at PSS coming from the Pegasus refinement project, from the Swiss project. There is an Italian model in Lucy et al. 2014. There is some models from the South Africa and the Hanford project, and they're either constant, magnitude dependent, distance, or magnitude and distance dependent. All right, so a little more description on the existing models. So the Pegasus models have used a global data set with data from California, Switzerland, Taiwan, Turkey, and Japan. Minimum magnitude of 4.5, maximum distance of 200 kilometers. They observed no regional dependence of VSS and proposed three types of models: constant, distance dependent, magnitude, and distance dependent. For the South Africa project and the Hanford project, they are very similar VSS models. They are also based on the Pegasus data set, but they are magnitude dependent. For SWAS, we had several models for Diablo Canyon, and that's basically because there have been different magnitude and distance ranges that were important for the hazard for the two power plants. So for Diablo Canyon, we have two constant models and one magnitude-dependent model. These models are based on the NGA West 2 data with magnitude greater than 5, distance less than 50 kilometers. And these models are looking at either California only or all the NGA West 2 data. For Palo Verde, one model is for the distance sources, and it's only applicable for distance sources, and it's constant with magnitude larger than 5.5 and distance 200 to 400 kilometers, again based on NGA West 2 data set. For the more local sources, there are two constant models. One is based on NGA West 2, one is based on European data from, not Atkinson, not Abrahamson, Akkar et al. 2013 at short distance. The Lucy et al. Paper has three VSS models for the Italian data. They're basically three subsets of Italian data with magnitude 4 to 7 and distance up to 200 kilometers. There are other models that I haven't looked at for now to compare with, which are the BC Hydro and the Hanford model for subduction earthquakes, but that's something I can do in the future. All right, so for VSS, I look at the SENA data, and again, I try to see which magnitude and distance range I'm going to consider. Given how many recordings I get for different min and Rmax, I decide to take min3, Rmax 400 kilometers, and that gives me the VSS values in pink. I fit that with this kind of a shape, and here I compare it with the VSS from the NGA West 2 data for Abrahamson et al., but for the same magnitude distance ranges, and again, short period issues. So let's compare now this constant SENA model with existing constant VSS model. This plot here shows the SENA in black compared to the Pegasus constant model. You have the central model, the upper and the lower estimates, and yeah. On the right, we have the Italian three constant VSS models. Now, here on the left plot, I am comparing with the Diablo Canyon constant models, and they are the red ones, so central, upper, and lower, and the blue ones. On the right, I am showing the Palo Verde models for short distances in blue. For large distances in blue, for short distances in red and in green. And the difference there is two different data sets. For magnitude dependence, for the model that I'm proposing is, again, same approach as for phi and for tau. Take the short distance and draw a line there, and then for the large distance, I am going, one option is to extrapolate based on the slope that I see with the Abrahamson et al. PSS for the same distance range and make it constant beyond magnitude 6, or force it to follow the same PSS at magnitude 6 and larger. So this is for 0.01 second, 0.1 second, 0.5 and 1. So these are the new SENA PSS models that are magnitude dependent. They are in blue. So I compare these with some existing magnitude-dependent PSS models. So there is the Hanford model in black for magnitude 5 and above, and the Swartz magnitude-dependent model in red. And so you see where most of the applicability range is where we don't have data and it's purely based on extrapolation. I show here there is an existing distance-dependent model, and this is the Pegasus model. It's shown here in black. However, this model, if I remember correctly, it wasn't favored after it was developed. In blue are just the results that I get with SENA. I'm not going to try to even propose a model or anything there, but just for comparison. Magnitude and distance-dependent model that was proposed for the Pegasus project is shown here in black for PDA, magnitude 3 to 4, 4 to 5, 5 to 6, and 6 to 7. And just for comparison, I show the results for SENA. And that's for a period of 1 second. Okay, finally the summary is these new models have some issues. Small magnitude, large distances, size classification issues, short period, so more work is needed. So I'm not sure that the results will necessarily be a lot better because we have limitations. I put there that the constant models may not be reasonable to apply everywhere because of the fact that the databases is biased to smaller magnitudes. Magnitude-dependent models may do better. You agree with the extrapolation. So to do is, Justin is going to revise the regression. He's going to try to get rid of the trend of the pi data versus distance by probably putting a Q specific. I don't know, am I making that up? No, it's true. So we'll see that may help. We're going to look to see if there's anything that can be done with the short period limitation of the TA data. Then again, I probably will try to use N-min3 instead of 5 to get a bit more data, maybe increase our max to, I don't know, maybe 600 kilometers, see what we can get. And then the pi is, we're going to see if we can correct for these past similarities and maybe try to use them because they're a big chunk of the data set. And finally, we'll probably do a more thorough evaluation of the existing models later. Yep, that's it.
Everything you wanted to know about sigma, right?
And yeah.
Some questions that were not asked during the presentation.
I think Gabe has a question.
Of course. Where's your microphone? What did you do? Okay.
This is actually for Gail and maybe Linda at the same time. Gail, didn't you at some point propose or demonstrate that sigmas were equal or lower in the east than in the west?
Yeah. Yes.
Yes, I did an empirical study in the Charlevoix area. Now, of course, that's a controlled data set, right? It's in one region, and the site conditions are relatively more uniform, so you don't get a lot of, I suspect that often what you see in sigma, and it's kind of a long-standing beef of mine, I guess, with sigma is I think a whole bunch of other things get cast into it, and I'm sure that's what's happening here, is that, you know, you see the sigmas going up because you have a whole bunch of effects that are in there, and there's no place else for them to go but into sigma. So, yeah, if you look just at data in the Charlevoix region, you get smaller sigmas, actually, than you do for the
Do you
West.
remember which period for that? I think I had it in the last workshop. I didn't look at it now. Just a couple.
That's for periods all the way from, from 1 second to, 0.1 second or 0.05, where you have data. The sampling rate of the instruments in Charlevoix is 100 samples a second.
A little bit. So I think we have that problem again because of metadata issues, because of a variety of site conditions.
Yeah.
And of course, in terms of site conditions, we have to remember that we're predicting for a very specific site condition. We're supposed to predict for a very specific site condition, but the data come in for all possible kinds of site conditions. So it's a tricky problem.
Yes.
So in the GMP working group, we only really focus on median because that's what we wanted to have as median model. Are you asking to get their sigma predictions and models, or yes? Asking? But do we want to get the sigma? Well, we could just do residual, but the sigmas from the modelers. Those who are modeling, if they're doing that as part of the modeling as well. The new model. Okay. Never talked about it? I don't want to add scope. I'm not adding scope, just asking. No. Okay. Thank you. Good. Next. Who has a question? Comment? Okay, well, this is great. That's it? Huh, man, everything is solved. So, point 3 and point 6. And some logging. 5 minutes or no more? That's done, right? Okay. Okay, so we'll do the recap right now. Get that done, over with. Okay. And then
Okay, as a reminder, we're trying to capture discussion items, not things that were presented. We don't have to go over those if they were already captured in the presentation. And anything, if we're going over a topic and one of your comments isn't captured here, be sure to speak up and Christine will add it in. Okay, so we're running through the GMPs that were presented today first. The Kramer and Al Norman model, one issue was the distance metric. I think it was set at epicentral distance, and we got to get something else in there so that we can apply it, either a conversion or switch to join your bore distance or something like that. So that
you were open to our RUP, right? No?
Yes,
it was
that
open.
would be
Yeah, it's
easier.
better. Yeah.
Okay. Intensity data, there was a question about is there a change in instruction quality that would make the conversion change from MMI to ground motion change with time? I think, I didn't write the response, but I think Chris said not really.
Captured, right? Captured in the,
Captured in what?
in his modeling, in the adjustments over time.
Do you have a time-dependent part of your model? No, there's no time-dependent. I think he said a lot of things were built in the East that are still there, and that their building codes haven't been. While they change the codes, it doesn't change existing building stock.
So you don't think it's significant? Is that your answer? Okay.
Can't get at it even if you wanted to. Okay. Whose data question came out about what is it? It is seismoscope data, and you turn it into a peak value, right? Is what? Yeah. So that's fine. Uncertainty in the historical magnitudes, I guess, was the main discussion we had in that topic, and in terms of something that may actually be done, that these could be pretty potentially large. And so really I think the best thing would be if you could rerun it, trying a different estimate of the magnitudes, just sort of moving them up and down, particularly treating them as correlated, right, so that we can see how much that changes the rest of the model. Okay? Anything else for Kramer and Al Norman? No. Next. Vladimir. Okay, so we were talking about why are you running both sets of data sets where one is intended to replace the other, and I think the main answer was the EPRI model had already parsed through it and eliminated the questionable sites, so you didn't have to do that. Ideally, that's in the other data set, but that takes more effort to do because you need to go through all the flags.
Select, delete.
Right.
But
so,
sorry.
Just so that we know why that's done, it's not that big of a difference anyway on his answers, which is encouraging.
Okay, but for moving forward, there's no point in carrying the old model. I mean, the data has been replaced. Is there a point in carrying that in?
So, Vladimir needs...
That's good, but that's a nice topic for a paper and a discussion, but does it need to be considered as a proponent model is the question.
Okay. Does it need to have 2,000 point source models?
What? Excuse me?
Okay. You know that, for example, Gail presented point source models, a lot of them. Okay, you can also say pick up the best model or choose something like that. I mean, my answer right now is pretty simple. Since both models behave pretty well relative to the databases, I don't see the reason to discard one of them. I may change my mind, but that's my answer right now.
That's fine, and that's also a question that I had for Sharam, and that's something we can address maybe in the weekly calls or separately. But you know, like EPRI, if we take the 05, the 11, or if the 14 model completely supersedes the old models, we don't need to carry them through. But you mentioned you wanted to carry one because of different geometrical spreading. So, okay, so we'll flesh that out. Yes, Bob has a comment.
Well, I think we should just ask the developers if this supersedes your old model, then we'll drop the old model out. If it doesn't supersede it, then we have to keep it. So
did you hear the answer? The microphone is dead.
The answer? What answer? I didn't hear an answer.
I didn't hear you.
I want you to go like this.
The end of the day.
Okay. My suggestion is that we ask the developers.
Yes.
Is your model superseded or not?
Yes.
We have a list of all the old models. We'll say we did the same thing in every 2013. If it's not superseded, then it gets dropped in. This isn't I mean, Nico's going to be sampling hundreds, and what's another 100
Oh,
models?
yes. He's going to sample the 66 from Dara, Silva, et al. So, yes, as well. Okay, good. Thank you.
All right. We also said residual plots. I think this would be a comment for everyone building models. Will be helpful to us if you can make them, particularly dividing it into the between event and within event residuals. And Vladimir said, yes, he understands it would be helpful. The question is, can he get to it or not?
And the project should provide them with a template.
Why don't you write? He's suggesting a standard template or format for submitting residuals to us, a residual plot. Okay, one of the questions on the Q terms, I guess, on Vladimir's model is using a constant Q, right? And how is that extrapolated to high frequencies? And I think the response was, well, there's really limited reliability in all the Q models at high frequency. Is that's all right? So Vladimir saying yes. Standard deviations, one reason they may be bigger than what we've seen in other models is because they're just fitting one shape, right, all at one shot, so there's less free parameters to work with, and you can't have as good of a fit for each of the parameters at once. Difference in the magnitude scaling, so that was part of the discussion that for magnitude 5, Western U.S. was larger than in the East in your model. Right, the Eastern model was lower. It was similar at magnitude 6, 7, and 8, but the 5 was showing a bigger difference. And the discussion is, well, if the data are at 5, what's the basis for it being similar at larger magnitudes and being different at 5? It could be, though, Gail talked about the differences due to VS profiles, Bayesian effects, and so forth is why that might be there. Okay, but that in general, his comparison between East and West is in the first order consistent with what was shown in the HA14 model. Okay. Anything else on Vladimir's model? You think that captured what we talked about while you were presenting it, Vladimir? Okay. Next, hanging wall effects. So several comments. Does a change in static stress drop get between East and West? Does it fit with the hanging wall model? And the answer is yes. It's sort of already incorporated in the way the model parameterizes itself based on down dip rupture width and where you are over the rupture. Frequency dependence, yes, it's there. The results were shown for PGA, but there is effect is seen at other frequencies and reducing at longer periods. For documenting this model, we do have the appendix that we will, from the Swiss report, that we can post. I think that's the first thing to do. And this, maybe it will end up as a peer report, USEF, or something like that might be the way to deal with that. So I think once you write in there, turn it into a peer report, because it should have a little better documentation or access, easier access, I would say.
Publish.
Hazard significance. So part of the question is this worth the bother, maybe is the way to put it here, of going through adding hanging wall effects onto our models when we don't really have a lot of faults that are known. And part of this is it's kind of easier to just do this in terms of making it available. You can always ignore the hanging wall part of the calculation if you're doing a hazard and you don't want to have that in there. But we've seen on even other areas with just background zones, ignoring hanging wall completely and just using a footwall-based model can lead to an underestimation of the hazard. RB model comparison, so there's a request from John to show really plots comparing the joiner bore-based scaling and the rupture width plus hanging wall effect scaling in a consistent way. That was done in the peer report, so maybe that would be adequate, because that shows it, I think, what Jennifer Donahue had done before. Is there a better distance metric to use? Probably yes, but at a computational cost that right now we're not willing to pay, so that we're going to stick with a more complicated adjustment with a simpler distance metric. Anything else on hanging wall?
Okay.
No.
Party time.
Albert, there wasn't a whole lot, so I guess there was, and see if I got this right. Gabe, you wanted to compare the non-stationary stationarity factor in your 87 model with the Van Mark model. Is that correct? That was a suggestion. Okay. I don't think there was any other specific thing. Albert, do you remember when you were up there, was there something else you thought people told you they wanted to see?
We can't hear you. It doesn't count.
I suggested, and this is a mild suggestion, and it doesn't something you don't have to do, but personally, I think it may help. Instead of the Bohr-Thompson adjustment for duration, use the one based on Coriolis and Van Mark that has the one minus an exponential term with the damping and the duration and so on.
Did you capture that?
No, I'm sorry, I was spacing out. I'm honest here. I'm sorry.
I think it's clear.
Adequate to what we've written?
I think it's clear there. Yes.
Okay.
And if there's any doubt, and if Albert wants to do it, and there's any doubt, we can talk.
Right, Gabe and Albert to work out the details. Okay.
Okay. Gabe.
Okay, did anyone else have anything on the summary of RVT and what's being done? Okay, next, finite fault simulation. So I put this up, first of all, just I didn't discuss this, but version control is a big deal for us. We're trying to move these simulations to make them repeatable and checkable. So that version that's being run now needs to meet.
Yeah, they're doing that right now. They're packaging.
Lockdown on SSHAC, and it will exist so we can go back if we need to and check it. The dip and the bump in the below 1, so in the sort of 1 to a half hertz range, I guess it was there in Graves and Petarca goes away. Rob said if they use a different velocity structure, implying that it's related to the structure and surface waves and not the mechanics of how the high frequency and low frequency was put together. Is that correct? So Rob's saying yes. Okay, then Art's basic comment saying, why are you doing this? This is the wrong approach. There's limitations of this, of using Fourier amplitude spectra for simulations as a scaling. We're losing the phasing information, not conceptually right. We should have confidence in the absolute values and use them and not just scaling them. So I put my but, okay. We have to deal with, I should put also here, once you put under the first, the validation. Right now, the simulation methods we're using didn't pass the validation requirements that we gave them for amplitude. So that's really why we can't use them at that point. I still, I think we're finding the FAES gives us a better method to incorporate seismological constraints into ground motion without all of the problems, especially at high frequencies when we go to response spectra and saying, 100 hertz response spectrum isn't 100 hertz Fourier or energy. And that's still been a difficult thing to keep track of, so I think it's better understanding, and I would, at the end, really converting Fourier spectra to PSA with RVT works pretty well for the average. I mean, it's one of the stable things that we think we know how to do.
But on this topic, Norm, so we're also doing in parallel the PSA model for sigma and all that. We can take the amplification factors in PSA and make sure we're not missing anything.
Right,
that's fine.
But we're going to have to document in our reports and so forth why this makes sense, okay? Because Art's not the only one who's going to have this view of things.
But we can also show if it makes sense or not. That's my point.
Okay. Making the information available from the simulations to other developers, such as I know Vladimir wants to see this stuff so that they can use it. So these magnitude scaling plots and their digital values should be made available, and I wrote your 1 week, so by the November 7th.
Already gave half of it.
We will get them posted so that it's available to everyone who's developing models. Anything else on the simulation?
Well, we need to decide what models we're going to use, if we rerun simulations, if we need to go to different distances, or we just need to make a decision on that. So that's a big item.
John.
John Ellis, Geological Survey of Canada. Where you see different velocity structure implying...
Could you put it closer to...
Sorry. Where you're saying, implying this is related to surface waves, I guess I'd like to be sure that we know those are important in the East. Okay? They can't be dismissed by going to a California structure. And the second comment, which is related to that, is I think the Z-Tor equals 0 data from fault simulation is really important.
Yes.
There isn't much other information for those.
So we only showed the subset, but yes, we have Z-Tor 0, 5,
why
and 10.
didn't you put in there, just at the bottom, evaluate the surface rupturing simulation? Yes. That's what you're getting at, right? I think the issue of surface waves is really for Rob to explain that he's not saying actual surface waves are there. It's from the 1D structure. Is that correct?
So the point I was trying to make or try to understand is that the features that are seen in the results are related to the assumption of the velocity structure. So I had done a simple test just replacing that velocity structure with a California one, and those features were kind of smoothed out. But I'm not proposing that that is the real structure. I know also that Art, in his presentation, had talked about this issue with the surface waves, and do we really believe that, you know, a 1D model extending out for many kilometers is appropriate? Maybe more so in the east than in the west, but I think that's still an open question. So I'm a little uncomfortable seeing those features in there, but I'm confident that given the model, that's what they produce.
So you can explain those features is the bottom line. We talked about maybe potentially smoothing through those.
Yeah, and I think that would actually be reasonable given how simple those velocity structures are, and you know the uncertainty in the whole process there.
Norm, just one other thing. I thought I heard one of Art's comments was something that maybe isn't captured here, and that as far as the range of distances that were being utilized in the finite fault simulations for the large magnitudes, that to understand the scaling properly, we might need to go out to multiple source dimensions.
So that's in future work. I'm going to start a new slide. Right there. Okay.
So basically implement the finite fault simulations out to larger distances, not just to the 70s.
Yeah.
For the large magnitudes.
Christine, what do you mean? Future?
Yeah.
What?
Future?
Uh-huh.
Oh.
I want to make sure.
Yes. It's very near term. So I thought so I'll put that bullet in a second, but could we handle that with other models? As you go 100 and more, I mean, is the scaling from the point source good enough? Or we need to, because the problem is realistically with the finite fault, the domain becomes so big.
It gets expensive to run.
Expensive to run, takes time. Yes.
I thought one suggestion, I think, Art...
Closer to the mic, it's tired.
I thought Art suggested select 2 out of 4 and move on.
Okay, well that's a different, we're talking about two different things. Talking about extending distances to larger distances, and do we even rerun anything is the bottom line. Okay.
Right, but if you're running these things out, another round of simulations is done, or we're simulating a bigger case here, that we don't have to run all 4 models.
Yes.
I think that's what the suggestion was.
So what do I write here? Consider...
Well, he wants to consider running, implementing the finite fault simulations at larger distances, because I think what Art is getting at is they could be these big magnitudes attenuating at a different apparent geometrical spreading than what we would have had for our magnitude 4s to 5 that we have to calibrate everything. Is Art still here?
No, we left. So we can consider that. Now, moving forward, so we have two methods that work. Is there a range in which we want to use SDSU, or we want to use only methods that work for the full range?
This would be focused on just the larger distance range here.
Yeah. I moved on from that point to another topic. I'm sorry. Okay. Next topic is, do we need extra runs for the platform for the two methods we have? And do we, let's talk about the 4 methods we have. Do we even consider the other 2 that had features we could not explain for scaling at this point?
So what would you do in addition?
Nothing. We're fine. We're done. Okay, moving on. I don't want to add. I'm just asking. We're here as a group, so if there's people who have concerns about, you didn't consider, because we go from 7, 5, and 8, and do we want to have some 7 in between? Because now it's pretty crude, and is it good enough? Do you want to go? We go from 5, 5, 6, 5, 7, 5.
I think the scaling of rock.
So one other thing that I briefly examined when I was looking at the effect of the velocity structure was also the effect of footwall versus hanging wall, and in particular at the longer period. So this is kind of different from what Bob had talked about with the hanging wall effect. And again, there is a sensitivity such that on the footwall, the surface waves at the longer periods tend to be more coherent, and you kind of accentuate that bump or those features, at least in the couple of tests that I had done where I did sites on the hanging wall. So, considerations, I would, in a perfect world, I think I would like to see hanging wall sites at some distances as well to do the simulations.
And is to hanging wall at large distances, or what do you?
So when we ran it, so we did a first set of runs in August, right? And we didn't share with everybody, but we looked at that, and we looked at hanging wall and footwall, and there were systematic differences. So we can have done it. Is that enough for you?
It may be, but actually, and this issue, so kind of tying on to what Art had said here, for the larger magnitudes, as we go out to
70,
some
50, whatever.
Well, and maybe we need to go out to 150 or 200, and I actually would like to see if this kind of difference on the footwall and the hanging wall side kind of, or they asymptote to one another in a sense. I mean, it's the same thing like, when we had done the simulations specific for the footwall hanging wall problem, and we wanted to make sure that we went out far enough on both sides so that you could kind of see where those tails started to merge, right, or where that effect dissipated.
Yeah, but we're not attempting to repeat, so I don't want to shut down the idea, but we're not attempting to repeat this. I mean, for NGs, okay, let's focus.
I know.
GMP is done in 6 weeks, completely
Exactly. 5
packed,
weeks.
done.
5
Yeah,
weeks.
5 weeks, yeah.
We have 5 weeks, so it means we have to run, we have to digest
Post-process.
the magnitude scaling, we have to pass it to GMP developers, they have to incorporate it, and by December 7th, they give us. It's impossible.
Yeah, no, absolutely. So that's it. We move on. NG is 2. Just computing the FASs from these time series is days. So, okay.
That's a no, Rob.
Thanks for translating Christine's Canadian.
I was very polite and unclear.
Canada speak.
I'm known for my tact, that's for sure. Okay. Next topic.
Go back to a bigger screen so I can see that.
What do you mean?
Okay.
Bigger. It's because
All
you
right,
write too small. Okay. Okay.
Okay, one was the magnitude dependence of geometrical spreading. So in what Justin ran on the regression, used magnitude independent term, right? Did you, and so this empirical data is only for small magnitudes. Have we seen a magnitude dependent apparent geometrical spreading term in FAS in California or in the simulation?
No,
Yeah, in FAS we did. In the first study we did with Yale, it was based on the modeling of Fourier amplitudes for moderate to large earthquakes from various regions with magnitudes larger than 6 and from various regions and magnitudes larger than 6. So we did observe saturation effects.
So I think what Justin's doing, he needs to allow that term to be there.
Yeah, we talked about this with Justin during the break.
Okay.
And I referred to him our paper, which is now published in BSSA. The thing is, I'm thinking of, because he's not observing any effect of different saturation models in his simulations, because the first thing is he's trying the NGA West2 saturation models, which were derived from PSA. And the second thing is he's calculating the residuals for the available empirical data, which are only magnitude less than 6. And the models he's using show saturation up to less than 10 kilometers, and we don't have data. So you can't actually observe such effect with that limited data.
So it may be the approach is back to pulling the Western U.S. amplitudes in there, doing a joint regression for that term, and allowing for some regional differences.
Yeah,
right?
we recommend this saturation model, magnitude-dependent saturation model I presented yesterday. So it provides an overall agreement with the empirical observations from various regions, including West.
Okay.
And
so to capture that, let's just say we're going to look at again the saturation model. We can compare to existing published studies, but that is correlated with the short distance saturation term as well. Those things are trading off.
Another point I want to point out here is in empirical regressions there is large trade-off. So like when you change one parameter, the regressions just calibrate itself to minimize the residuals, right? So to select the best geometrical spreading term with such limited data, I think the best option is you can constrain if you are working in Fourier amplitude domain, you can constrain your selection by the known seismic moment. For example, you try different values of geometrical spreading and calculate the source spectrum for each trial of geometrical spreading, and you determine the seismic moment implied from the source term you get from regressions and compare with the known seismic moment of that specific event or overall to get one specific value. Of course, this method only useful when you assume that geometrical spreading is independent of frequency, because you're running for all frequencies with the same geometrical spreading model.
Okay, so I think, and you've got here too, I would say we just got to check the previous published approaches.
There. Mm-hmm.
Okay, hypocentral depth dependence is correlated to geometrical spreading. That's sort of what we were just talking about. and it was seen a depth dependence seen in the YA models, right? Anything, let's see, you had the next page?
I have another slide.
All right. So one of the key things is we talked about our whole issue of what is our reference site condition in this empirical model since the site terms are taken out. And right now it's with all stations, but that we need to look at limiting that to the well-behaved stations and then doing our correction. And whatever we do, we need an analytical correction for FAS to 3000 and a kappa 0.006. Then how much does magnitude scaling match up? So
yeah, just looking at.
We need to plot it, and then if it's not smooth through that transition. Okay. Anything else on the empirical FAS model that Justin showed?
Okay.
All right.
Duration.
Okay. So for Nico's duration, effective source depth on duration, it was there, but small, I think is what he said. Differences in duration between east and west. At large distances, longer durations in the east. At short distances, longer durations in the west is what he found. And right now there's a bias in the between event residuals for PSA. And up
norm.
Correct.
We fixed that.
Okay. Already?
Yes.
All right.
Yes.
It's been fixed. So just say this bias has been fixed. Okay. Or done. It's already done.
Has been done. Do you agree with the empirically matched RVT duration? Has been removed.
I don't see what you're talking about.
I changed it. You called it duration, so I.
That's fine.
Okay. Okay. Next.
We're going to give it some new term, right? That was the next thing. Come up with a new word for this. Is it the DRVT? Is it something else to make sure it's a calibration parameter?
Oh, there you go. Empirically matched RVT duration.
Yeah, but nobody's going to,
No, we got to work that out.
We'll work out another name that's a short answer. Because people aren't going to say that. That's not going to roll off your tongue. All right. Anything else on duration model? No, we're getting near the end of the day. Proponent model. Oh, so this is the Salmon's map. So for the plotting tool, we need a button to select all and a button to clear all, clearly, to speed that up. That became... Salmon's maps. We're adding units to the axes. Hooray. Okay. So
thanks,
Gail. Current units would be natural log units, and we're going to normalize by number of scenarios.
What?
You want the title. Okay. Units and title. Okay.
And title.
If we normalize by, let's say, root n on what's there right now, then we'd be looking at essentially, and that the distance in the map space would represent the standard deviation, the differences between the GMPEs at the selected scenarios. You do, otherwise you're just summing it up. I calculate the standard deviation from, if I do some of the scores of 10 points or some of the scores of 100 points.
You're not allowed to without a microphone, please.
Gabe is arguing a losing point here. So we
of course, he has no voice. He's going to lose. Okay.
No, he's just summing up the difference, and that sum is going to depend on the number of discrete magnitude and distance pairs. If I double them, if I took every magnitude or every half magnitude, I'm going to get a bigger number.
But you don't plot that. You plot pointwise. Yeah. Okay.
We'll make sure the unit, if there's units, then you can get your ruler out and measure it on there and see that it is similar. Okay.
And check with the 28 dimensions if it matches.
Add in some direction signs, so road signs on the maps, okay, with M magnitude scaling, the R scaling. We did that in some of the earlier workshops. One thing is we can use the YA14 model as an efficient way to crank that out and give us some directions and drop them in there. We do need to consider alternative measures for the similarities of the GMPs. That's a fundamental thing that we're using on the salmons maps, and we don't want to just say Euclidean distance is the right thing to be doing. Either we could look at other norms or how we're selecting the MR scenarios that are most relevant to hazard and so forth, but that just needs some more thought, and we need a justification, I think, as to why we've chosen a particular metric. Because carving up that space is the fundamental approach to this whole method, that space and in those units is the right thing to be doing.
Also, did we talk about thinking more, so what's important for hazard, but also just what are we trying to capture? We might have more than one set of maps, magnitude, distance, range. I guess that's fine. The second point covers it. Okay.
I think what you could do is select models in one space and then see where they pop up in another space. But we can't.
No, we can't.
You got to do it one
yeah.
time, but we could check it in other maps. Okay.
That's a good idea.
Second half of this. Okay, so a map is made for each period. So the representative models are selected for each period. Again, meaning that we don't have a single model that is applied at all periods. In our break discussion, we were saying, well, that's actually similar to the way the GMPs are derived. If you estimate one coefficient at a time and don't smooth across periods, it's similar to that kind of an approach. So it will lead with, it's like no smoothing, so there will be a bit of a jagged mean spectrum that comes out. Smoothing could be applied if we chose to do that, but hazard analysis tends to smooth things out anyway in the end by the time you apply it. Okay, you wanted to
also, I guess, I don't know how you solve that problem in SWOS, but don't you also have the problem that the weights may be different frequency to frequency? So there's no correspondence.
There's no GMPE that you say this one is the high one at all of the frequencies, or this one is the low one at all of the frequencies.
Okay, so there's smoothing. You cannot do GMPE by GMPE because there is no such thing.
No, but you could smooth the mean.
You can smooth the mean. Okay.
You could get the mean weighted model and go through and add a constant at every period to come out with something smooth. I'm not sure it's worth it, but that's what you would do. So I would just say we need to show that the resulting shape is smooth enough or reasonable in terms of the mean. We are doing simplified hazard, and its use is limited just to picking the GMP. We're not telling you what the hazard is at the site. It's just a way to focus the selection of the ground motion model in terms of its hazard relevance for something that's representative. So we're trying to get something here representative of a source characterization for the entire eastern U.S. And we could use the average of the 7 test sites. It'd be one easy way to do that. Or we run it at 7 and we find the model whose hazard is closest to the mean at all 7 sites. Okay, but I think that's manageable.
But if it's in the cell anyways, it's in the cell. We're already
correct.
So it's
right.
Just being more,
trying to give us a way to pick, instead of random in the cell or an average of the ground motion in the cell, averaging it by hazard. All right, next. Anything else on salmon's maps? Are they making more sense? So several of you have seen this 4 or 5 times now. For those of you who listen, it sounds like a lot, but I think when we get the units and the labels on there, it will make everyone feel a little better, and you should be able to really get the interpretation of what's going on.
Okay.
Larry.
Larry Salomon, Joint Management Committee. We just raised the issue about redoing it for the Gulf, since right now the Gulf is not in there for the salmon maps.
So
I think our official answer is the Gulf Coast is out of scope. Is that our official answer?
the official answer is that we may address the Gulf Coast with correction factors, but we're not, So, but if we do that, if we address it, we'll, absolutely separate map, if we do it.
One related comment on the Gulf. In this latest work we did in 2013, with Martin's model for kappa, the difference in Q between the Gulf and the mid-continent became much smaller than it was before. So that may justify having the Gulf as an add-on instead of doing it as a purely independent model.
I think that's what Christine's
That's what
saying,
I'm
another
trying.
factor that we can put on.
I'm reinforcing that as a viable.
Okay.
So, but if we do, yes, we can put that. We can show where it fits on. Okay.
Just right on here, just so we don't forget it.
Okay. Yes.
How treatment of Gulf Coast as a added term to the model and not a completely separate model. Right? It's going to be the practical way to get it done.
Which is still shown the map on its own.
Sure, it's easy to do.
Yeah.
Once you've made it, it's easy to do. Okay, anything else on Salmon's map? Okay. Sigma, so I don't have a whole lot on Sigma. There's a few things. So 10 hertz bump, so starting with tau, that we've seen in the west is also seen in tau for the east, but it's not sort of matching the expectation that if that's kappa driven and by smaller kappas that it would be shifted to higher frequencies, but that may be just due to the limitations of the bandwidth that has been averaged out currently. This is back to a recurring thing. We need to be applying some frequency limits in terms of what we're doing for the standard deviation. You should, Linda, replace the EPRI tau model with a new average value model for
if
NJ
needed.
West 2.
If needed. For the EPRI, you don't want to repeat that, or just that if you really want to look at it, repeat it.
Okay, go ahead and write if
So
needed.
if needed, just add 2 words.
That's fine. I just wasn't sure where.
And then just a general comment that we need to just keep in mind is anything more complicated than constant really justified given the available data.
One comment. Is there any concern? Well, actually, maybe the constant tau solves it, but is there any concern about the fact that the tau has the different trends with period in the east and in the west?
So
Tau goes up with period in the west, and it's going down with period in the east. And why is that happening?
Why is that?
Try to
That
understand.
could be,
try to understand. And
did you see that for the smaller magnitudes as well, Linda? Yeah.
I haven't. Yeah, I don't know if I looked very carefully. I should look at this again.
For a common magnitude range, because we'd seen some funny behavior of tau at small magnitudes at long periods. It got really small in the west as well for the magnitude 3s. I think it came crashing down. Okay. Anything else on tau? Okay. Does everyone remember what tau and T are? I gave you a test. Oh, you're going to. All right.
He's the old sigma.
That's
Emra,
true.
yes.
Yes.
You see, we're awake. Emra, can we give Gabe, please share. Thank you.
I'm wondering if that significant tau at large frequencies, high frequencies, or short periods is due to significant variation of stress parameter we observe for small magnitudes, which is also depth dependent.
I think it's going to be hard to resolve with the data we have, because the problem is 90% of our data stops at 16 hertz. And then there's a set of data that's only from Canada, mostly, well, some from the U.S., goes to 50. So we can't really, we can look at it, but it's going to be
like, what if, like, they, I don't know if is it feasible or not, but what if they rerun the tau for our model instead of Justin's model?
Sure. So,
because it considers that depth-dependent stress parameter.
So we should take a look at those. We could take a look at those towels. So if you have them,
I don't know what Gail thinks, but
so she's thinking
You have them, so
yes. So Gail has volunteered after he hands in his thesis, he can run it. Okay. Thank you for volunteering.
We need it in 2 weeks.
Yeah, 2 weeks. Okay. Next slide. So
yes.
phi. So phi is the new sigma?
It's the old.
That's fine. The old sigma. So the main issue here has been, what Linda showed repeatedly, the large values of phi at high frequency. And we've got to account for the high frequency limits. And we might just end up, because of the mixed data set, end up running to 10 hertz and then doing some extrapolation up.
But that's for all the tau, phi, CSS, and all that. We shouldn't go beyond 10 hertz, I think. With the oscillator period, I mean, it's going to be hard to get something.
The other part was to try a more limited distance range to 100, say. Even though you're going to have a really small data set, Linda, just try it and let's see if that does anything. Because it won't be zero. There is something there still. Okay, anything else on phi before we jump to PSS? No. Okay. PSS, all I wrote was check the similarity of path effects for the for a smaller distance range for pi and not just that whole large distance range.
Yeah. Okay.
Anything else on CSS? Okay, and then next one, last was sort of some general things. So previous evaluations from Gail had for a small region in Canada then is showing a smaller total sigma in the east and the west. We need to resolve that before we start building models that show an increase. And then should the sigma from the new models be included? I guess I said no in general because we didn't want to deal with all the data set issues, but we just said yes for, say, the YA model. So instead of no, why don't you say some? If provided, right. If provided, because we need not just the sigma, we need the data, the underlying residuals, because we have to be able to see what outliers are doing and so forth. So why don't you put there, instead of a no, put yes? if the raw residuals are provided to us. So we need a soon.
In yes, if we get residuals within 2 weeks. No? But when?
No.
Okay.
2 weeks isn't going to happen.
Okay, very soon. In time. So we can look at it if we get it in time. If not,
time is going to be
December.
December. It has to be well before the January workshop.
Yep.
Okay. November is tomorrow, or in 2 days. That's really hard.
Day after tomorrow.
I think we're going back to no. No, but, no. We should say. I think, Linda, this might be something that if you're gone, someone else can run and still do the comparison. So.
Okay. Good enough.
One other thought on sigma, and again, I mentioned that earlier. You're predicting sigma for very specific site conditions, which in theory should reduce the predicted value. In practice, I don't know how you bring that in and how you incorporate that.
But we're running PSSs. That's doing it.
For 760, not 3,000.
So those sigmas for rock sites in Charlevoix are actually quite relevant.
Yeah. So I think our general, we should be isolating the sigmas from that Charlevoix data.
Sigma from sites close to reference conditions.
Yeah. Okay.
Cool.
All right.
Youssef is getting
So
antsy.
to
I can
reinforce
feel
that
him.
point a little bit, because otherwise you're going to count twice. if you get a high sigma, if you assume a high sigma at bedrock at 3,000 meters per second, then you put in whatever comes out of the side response. And
But
again, that's a
we're
question
giving
of
you single
PSS.
station signals. So
But the PSSs were high still.
They're high, but we can't. They've removed the average site term by definition.
Definition, if you have enough, blah, blah,
If
blah.
we've done it, well, I think you could look at another set of sites, and maybe they're going to be more stable than what we've seen before. My guess is more of this is due to the data processing, that we are mapping. If some data are filtered at 10 hertz and some at 15 and some at 30 hertz, that is just simply mapped into the standard deviation, and that could well be what's going on. All right, that's it.
Okay,
We are 5
that's
minutes
done.
over, so we need to...
Yeah, observers' comments, 5 minutes. I let you handle that while I copy things to the hard drive.
Okay, anyone in the audience, comment? Your last chance.
This morning I noticed the models, GFP models, often were presenting data up to 10 seconds. This afternoon I noticed all the analysis of the data was limited to 1 second. My question, or it is a question, I won't get an answer from it probably, is where are you going to limit the presentation of data, and if it is beyond 4 seconds, 5 seconds, that there is some reference to displacement, because the only thing that is of interest for users beyond about 4 or 5 seconds is the displacements, and that they better be consistent with the accelerations that would be provided if it's given in an acceleration format.
Providing, they only show plots for 1 second because we often will do a short period and a long period value, but the models will go for longer periods. In terms of displacement, everything we do in PSA is spectral displacement, right, in units of Gs. So we are dealing with spectral displacements, but not peak displacement.
Mm-hmm.
So those things all should be fitting together. So we're not, and so we look at how things scale. The spectra should be heading flat towards displacement at long periods and so forth. So depends on the magnitude. Not at magnitude 8, it won't. Magnitude 8s won't saturate till 20, 30 seconds. So magnitude 7s will saturate around 8 seconds. So there's a magnitude-dependent saturation that should come out of it. Yeah, that's... Yes, big magnitudes give you very big displacement. Larry.
Larry Salamone, Joint Management Committee. Just wanted to close by recognizing our host and the organization of this workshop. It takes a lot of work to pull this off, so I want to acknowledge that. I also want to state to the researchers who have developed much since the July workshop. Keep up the good work, and we look forward to you all completing your work.
Thanks.
Thank you, Larry.
Any other comments? No.
No.
Okay.
All right. So we are almost done. So before you leave, I would like to thank sponsors, NRC, DOE, and EPRI. We couldn't do it without their support. I would like to thank PPRP for their constructive comments and feedback, and we'd love to hear more from them. Qualified volunteers, Mesa, Sahar, Sifat, really they helped 2 days. Let's appreciate their work. Yolanda and Stephen, peer staff, they spend lots of time in the background printing all the labels and so on. We really appreciate their support. Especially I like to thank Norm and Christine. They spent tremendous amount of time for preparation of this workshop. We thank you both. Appreciate that. There are, as Christine said, there are about 55 people who have been working on various pieces of this project, from junior researchers to senior researchers, practitioners, and so on. I'm really proud of them. We really appreciate their efforts. We couldn't do anything without them. So finally, I like to appreciate your participation. This is officially end of SSHAC workshop. We'll see you in January. Thank you very much.